So today we're going to talk about something new, okay? We're going to take a look to what is called, the recovery and concurrency control. Okay, so today I'm going to just focus in the first part. How can we perform what is called failure and recovering the database? Hopefully, if you have a time, we're going to cover, the concurrency control. So generally speaking here, what we learned so far, okay? So at the beginning, we take a look from the beginning of the semester, we try to do what? To implement the database management system. So at the beginning, take a look here. At the beginning here, we did what is called, how the data file is going to be stored in the disk, yeah? Storage manager. Then after that, in the top of this one, we built what is called, the buffer pool, okay? So we covered, how, take blocks, for example, from the, from the disk and fetch to the main memory and, back and forth, okay? Then after that, we talk about access control. It will allow us to expedite the access of the data. After that, in the top, yeah, we build or take a look for example, how can we execute our query. So today we're going to take a look at two different components. The first one we call concurrency control, and the second one we call this one recovery failure. What do you mean by this one here? So let me give you like the motivation behind this one, so why we need to waste our time in order to take a look to this kind of components. Assume that we have one application, okay? And this application, for example, requires from you to transfer money from account A to account B, okay? So yeah, let me write this one here. So for example, you need to transfer money from A to B. Assume that you're gonna take $100 from account A, and you need to deposit this one into B. For example, when you, the transaction you're gonna use here is gonna do what? It's gonna read the data from, for example, the account A or record A, deduct $100, then it's going to deposit this $100 in account B. What happens if something happened in the middle? For example, after you deducted the money from account A, the system is crashed. So at the end, how could you recover from this one? Because the problem here, you deduct $100 from account A, but you didn't manage in order to deposit this money in account B. This is what we call, the crash, and how can we recover from the crash failure? This one thing. In other words, we need to make sure that how can I restore, correct state after failure. When I say correct state, either take $100 from account A and deposit in the B, or do something that it looks like that we never deduct the money from account A and try to deposit B. The second thing, or the second problem you need to think about, for example, assume you have two transactions, or let's say two processes, or the two threads, transaction 1 and transaction 2. Both of them try to access the same record. And for example, this is a record here. Assume this would be record 1. And both of them try to, let's say, modify, let's say, the same attribute in this record. So here in this case, since both of them are trying to compete in order to try to update one piece of information here, we need to make sure that if we have multiple threads or multiple processes or multiple transactions try to operate at the same, let's say, record, we need to make sure that the system is going to ensure correctness. What do you mean by this case here? We need to make sure that we are not going to lose any update. Because assume that, for example, what if transaction 1 is the one who's reached this record first, and the transaction 1 said maybe this attribute is going to equal 10. Then transaction 2 after that modify this one and take it, put it 20. Yeah, so it looks like we have a race here. Which one is going to arrive first? And we are not sure what's going to be the final value of this attribute that's going to be, modified by two more transactional process. So in this case, we need what is called a concurrency control or mechanism in order to allow us, the system, going to ensure the correctness. So today we're going to take a look at the first one. So take a look how can we make sure that restore after the system is crashed into what is called the consistent state or the correct state in the system. Failure recovery or crash recovery, we define that as what? As a set of algorithms or techniques that I'm going to use in order to make sure that the database is consistent, and also the transaction atomicity and durability despite failure. So in this case, that for every recovery algorithm is going to have two parts. The first one is to take a look, for example, it looks like we're going to go through some steps, okay, during the normal execution of your transaction. For example, we try to move the money from account A to to account B. The system or the recovery mechanism or algorithm is gonna do store maybe some useful information in a way that if any failure happened or if the system crashed, how can we use this information in order to recover from this? The failure that happened to the system or the crash. And remember, we try to achieve three properties: consistency, atomicity, and also durability. I'm gonna define this one in a few slides. So generally speaking, the database management system is going to divide into what? Into, different components. As you see right now, we do have like storage manager, take care of how the data file is going to be stored in the system as a blocks. Yeah. Then after that, we have what is called the buffer manager is going to take care of, is going to keep the data as what? As a pages, the main memory. Yeah, and etc. It looks like we have a different components. Some of them are volatile, some of them are non-volatile. I see that's going to start in the disk manager. It's going to do what? It's going to be blocked. So data is going to be non-volatile. If the data is going to be, or the pages in the buffer manager, we call this one is going to be volatile. So in this case, based on that, we need to keep tracking and understand how can these different components fail or maybe have a problem based on different types of failure, okay? That can occur in different stages and how the database management system is gonna react in this case. So at the beginning, I'm gonna take a look first or go through different types of failures, okay? And we're gonna see which one is gonna database management system can react or can handle and which one that cannot. Remember, we have different components, so the failure may be going to happen in different places, okay? So we need to make sure when we build our database management system, it can take care of this kind of errors or failures. And remember, we cannot handle everything. So just to give you a head up here, for the type 1 and type 2, we can cover. The database management system we're going to build, we're going to cover this one. The third one cannot handle this one. So let's take a look at the different types of failure and see how can the database management system going to react in this case. So the first one with the transaction failures, okay? And generally speaking, when you hear transaction failures, it's like occur when, for example, the transaction fails to execute or maybe when it reaches a point from where it cannot do anything further. And we do have many reasons for this kind of transaction failures. The first one, we call this one the logical errors. When you have a transaction, just a reminder, transaction is the sequence of this operation you need to perform over our database, yeah? Set, for example, if you have a transaction that transfer money from account A and account B, so that means read the data from account A, remove the data $100 or the amount that you need from account A, then after that, add this information or data or what, the balance or the money that you deduct from account A, you have to put this one in account B. So it looks like we have a sequence of structural or operation we need to perform. Okay, sometimes in these instructions I'm going to have something cannot complete, for example. Maybe there is an internal error condition. For example, you do have, like, we talk about the consistency in the database. When you say the database is consistent, that means the data that's stored in the database are valid data. All of them are going to follow what is called the constraint that we enforce in our database. For example, if we said the age or let's say, the GPA never being minus or negative value. So it's one kind of integrity constraint that you put in your data. So for example, if your transaction perform any insertion operation, or this insertion operation is going to violate what is called any integrity constraint or false in this data, in this case, transaction cannot continue. So there is an error. This is one kind of errors. The second one, we call this one the internal state errors. So the internal state errors, or sometimes we can call this one syntax errors, okay? This one, the database management system itself terminates an active transaction. For example, sometimes you're going to see that, I guess you are familiar with this one if you, the operating system course. You see that sometimes you have a different processes are going to compete, it's going to be perform what is called, the deadlock. So each of them is going to waiting for the other one in order to finish. I'm waiting, for example, process 1 and they're waiting for the information from the process 2, and the process 2 waiting for the information from process 1, or each of them waiting for the other in order to release any resource. So we're going to reach what is called the deadlock in this case. So the operating system, you have to handle this operation, do what? It's going to abort one of them. The same thing in the database management system. So database management system maybe can, terminate any transaction due to any error condition. One of them it might be we have, as I mentioned, deadlock, or maybe there is a resource unavailability and etc. Okay, so on both them, these kind of errors, the transaction errors, we have to build, or the database management system can handle this kind of errors. When you say can handle, that means if these kind of errors that happen, database can recover from this one. For example, you have a transaction, and this transaction composed of a set of, operation, yeah? Maybe you perform maybe the first, let's say 50% of this operation of this transaction. Then at the middle something happened, any errors or any logical error, so transaction must be what? Cannot be complete. So in this case, what you need to do, the database management system, when discover this kind of error, must roll back whatever this transaction made a change on the disk in order to make sure the database is going to be in consistent state. Okay? Anyway, we're going to see this one through the, starting with this lecture and next lecture, how the database management system can handle this kind of errors. Transaction failures, database management system can handle this one. The second kind of or type of failure, we call this one here, the system failures here. The system failures can occur, for example, due to the power failure, or maybe there is any other hardware or software failures. Okay, so let's take a look at the software failure. Assume in this case, for example, the database system is like, there's a problem with the implementation of database system. There's a bug in the code that we use in order to build our database or write our database system. For example, you can, during the implementation, you didn't encode what you call divide by zero exception. Yeah, it might be you divide two numbers, then since you didn't write your database code correctly, so in this case, maybe if this kind of error happened, so the system is going to be crashed, yeah? Because the database system itself is going to be halt. So in this case, how can we deal in this situation? We need, for example, to be able to, let's say, recover from this kind of failure. Yeah. What happened? Remember, when you work on your database, or database was running at the time, there's a many transactions going to be executed, yeah, or was executed at the time. So you need to make sure that you need to handle this situation. What's going to happen here, yeah? For example, you have two scenarios. What if we have one transaction was running at the time when the database system or the software failure, or the database, there is a bug in the database system implementation at the time, and for example, the transaction codes divide by zero, so the system is going to be halt. Remember, the transaction is going to be a set of operations, okay? You don't complete this transaction, so it's like you partially modify or update your database, yeah? So you need to do what in this case? You need to handle the situation. That means if I didn't complete this transaction, you need to find a way, a mechanism in order to roll back whatever this transaction did. Okay? If the transaction or the set of transactions commit before this error happened. So in this case, do you need to do anything here? In most cases, no, because I need, since the data is a commit, I need just to make sure that whatever the, completed transaction, any change has been made to the database must be possessed, must be stable, must be there, yeah, once we did, or must be still in the database stored. Okay, the second one, the hardware failures here, which in this case, when, for example, the machine that, for example, where your database system, for example, is running, is a crash. What do you mean by this one? Where which machine or where you're gonna store your database system, for example? Maybe you're gonna be in the cloud, or maybe there is a server. Okay, and at the server, something happened bad at the server side. For example, the power plug maybe gets pulled, or for example, in my case, my kids is gonna unplug, for example, the computer, or the power, the cable that, or power plug that connected to my computer. Yeah, or any reason, maybe there's the server that place catch fire or whatever. So in this case, we need to make sure that how can we handle from this situation? And we need to make sure that to do one thing, we call this one, we have one assumption here. If that happened, if this data or the system that hosting the database crash, we need to assume that what is called the fail stop assumptions. In this case, whatever kind of crash that's going to happen for the server or the computer that hosts the database is going to be recovered. In other words, it's not going to cause any corruption in my system. Remember, the database is going to be stored, for example, in the hard disk. If that hard disk that you, for example, that remotely hard or that resides at the server side, after lose the power, when you turn the computer, the server side must be work properly. That means it's not going to cause what is called, any bad segment or any unrecoverable damage. Okay? So that's what we call fail stop assumption. In this case, Can the database management system handle this kind of error? Yes, and we can do this one. We can recover this one. And I'm going to show you that for the system failure and also for the transaction failure, what the database management system going to do must be due during the normal execution for the query in order to make sure that they can recover from these kind of errors or the failures. The third type of the failure that we call this one disk failure, or maybe it's gonna be a storage media failure, or what, or another word we can say non-repairable hardware failure. So in this case here, this kind of errors or failure, the database management system cannot handle this one. When I say cannot handle this one, that means you didn't need to write your code, or for example, store some extra information in order to help you to recover from this kind of error. Because the problem with this one, for example, what if the disk or whatever, the hard disk that's used in order to store my database is crushed. In other words, the head is crushed. So that means you cannot retrieve any data from this hard disk. Okay, and these kind of errors, it's of course when the hard disk driver or the storage driver used to fail frequently, and used to have this problem was common problem in my days when you start working in the database. 20 years ago, most of the hard disk are unstable. So for example, the hard disk, maybe you will store your data. When you try to achieve the data of the hard disk, you get a bad segment or etc. The hard disk is not going to work anymore. Okay, so there is many disk failure. One of them, maybe the formation of the bad sectors or the disk had crashed. So this one is going to be what? Maybe it's going to destroy either all parts of the database or some parts of the database. I know someone is going to say, okay, we can do we can retrieve the data from the archive. Yeah, that's different. But in this case, that means when you try to retrieve your data from the archive, you are not going to store a piece of information. For example, you're going to see when you use the logging technique in order to allow us in order to recover this kind of error. In this case, when you retrieve the data from the archive, what we're going to do, just take the first copy of the database and store it in another place. So in this case, the database management system is not going to handle this kind of errors. Okay, so just to give you some examples, for example, of the failures that happen with kind of transaction. Assume that, for example, as you mentioned, we have a transaction, and this transaction is going to do what? It's going to transfer $100 from account A to account B, and this is the transaction. At the beginning, just ignore this system failures, okay? Fails here. So example, this is the transaction that we have. It looks like a set of operations you need to perform in order to do this job. And remember, since we don't have like a specific command we can use in the database system in order to tell them that please move money from A to B, you have to write your own code, in other words, or own transaction. So here, for example, read from the account of A, take the balance from the A, deduct $100, then write A, that means update the balance in A, that means balance in A must be modified or must be updated. In this case, it's going to be minus $100. Then after that, read the account B, the account balance, when you talk about the account B, whatever the record or whatever piece of information with the account B. Then after that, retrieve the balance and add the balance, add 100 to or deposit the money in the account B. Then after that, update the account B. So if in this case, for example, account A $1,000 and the account B, both of them $1,000, at the end of this transaction, the account A is going to end up with $900 and the account B is going to be $1,100. Yeah. What if something bad happened in the middle here? So now we're gonna see during this transaction, I just deduct $100 from the account A. Okay, then the system crash or fail here. Something bad happened. That means we need to find a way. We need to do using the recovery mechanism in order to allow me in order to recover this one. So the simple solution in this case, if the transaction is not hasn't been completed or commit. So what we're going to do here, you need to roll back whatever this transaction did. That means it looks like you try to find a way in order to reverse whatever this transaction did or modification has been done in the database. So here this problem is solved by logging, and we're going to see how can you perform this operation. Okay. So now we said, we need to make sure the database is going to be inconsistent state. Okay, what do you mean by the consistency? The consistency we mean that the database is going to be incorrect. In other words, or in other words, for example, the database must follow all what is called satisfy all the constraints that enforced in the database. So before we work with this one, let's take a look what piece of information we need to retrieve in the data. We call this one the database element. The database element, which the piece of the unit of the database is going to be accessed by the transaction or the database system. So in this case, for example, we talk about A, this is the database element, yeah, that we need to access. So generally speaking, we know the definition of database is a collection of database elements, all these elements, yeah, we can define this one. And generally speaking, many database systems, they're going to use different notion of the database elements. Some of them are going to define this unit of the for the database element as a relation, or maybe as a tuple of the relation. In our case, maybe you can use a disk block. It's going to be easy in order to simplify the process that they work with. Database state, we know that before from the CS425 of the database organization class, is defined as a collection of the values of all the database elements in the database. For example, all the current state, what's the current value of all the tables that we have in the database? Okay, this database state might be changed, it can be transformed from one database state to another database state by changing at least one element. For example, if the current database right now, all the information about the student, okay, username, first name, middle name, etc. Yeah, and maybe you have a grades and so. Then if you modify any database element, that's going to be transferred from one database state to another database state. Okay, so the database state can be consistent. In other words, can be correct. In other words, okay, if it's consistent, this means all the database elements that's stored in this database state is gonna satisfy all the constraints that are gonna be enforced in the database. When you say talk about the constraint, that's means, for example, you can say the GPA never be let's say negative value or never exceed 4.00. The age is going to be started from, for example, 0 up to, let's say from 1 up to 100. Or in other words, never being has a negative value, and etc. Okay? So if the database state that you have can be inconsistent, that means if they didn't satisfy all the constraints. And sometimes you're gonna see during execution, in the middle of the execution of the, let's say, the transaction, database might be inconsistent. But the most important thing, once you execute the whole transaction, the database must be back to the consistent state. So again, if you have, in order to modeling whatever the consistency of the database, or in order to achieve what we call the concurrency control and the recovery, we're going to achieve that using the transaction. So it's worth now we just to remind you with the definition of transactions and what's the property of the transactions. So the transaction is just defined as a sequence of a change or a sequence of operations, okay, to one or more database elements. So the symbol, and the most of the case, in the transaction, mostly we're going to care about the update, because the transaction is going to modify the data. If you are going to all the transaction, going to read the data, so we don't have a problem, yeah? So here again, the transactions are transfer A and B. This is, the transaction, the sequence or the set of operations you're going to perform in order to execute or perform the job that you're required from, or in order to execute a query. We can modify the transaction definition a little bit. So we can say the same one, that the sequence of the change, the same thing, or set of operations you're going to perform, okay, or in order to execute, let's say, a query, okay. And when all the change, that's the new thing that add in the transaction, that's being made to the database state. For example, this is the database system is going to be start in the consistent database, okay, or consistent, a consistent state. If you execute the transaction, perform the entire transaction, the transaction is going to do what? It's going to produce a new database state. Yeah, because the transaction is going to modify, do some operation, and modify the database system. So if this transaction modify the database from one consistent state after you perform the whole operation, this transaction must transfer the database system from one consistent state to another consistent state. Sorry, the database state. Okay. So what's going to cause, inconsistency in the database state in general? We covered this one at the beginning of this lecture, but let's do this one using the transaction with example. So there's two causes of inconsistency in the database state. One of them, it might be the system failure, and the other one might be concurrent execution. That means we have multiple transactions going to execute, try to access the same database system. So let's go with example here. So for this one, for the first example, I'm gonna see how the system failure maybe cause inconsistent state. Then after that, we have another example using the concurrent control. Execution, and see with how the concurrent execution of the thread. So let's say transaction gonna cause database is gonna be inconsistent. So the same example transferring from A and B. So this one from the A and B, let's take a look at the states that we have. The consistent state, when you start with, this is the current value of A, this is the current value of B. So the consistent state that we start with, what's the current value of A and B? And we assume the initial state is going to be consistent state. Okay? Or consistent. So when you perform this transaction, here, what this transaction do is going to take $100 from A and deposit $100 in B. So this one, if we execute this transaction completely, and we assume that it's going to be transferred the database from one consistent state to another consistent state. So the new consistent state is going to do what? A is going to list $100 and B is going to has extra $100. So we start from A and B. When you perform this transaction, this is the other transaction. So that means if something bad happened in the middle here, and I start from A and B, I never reach A minus 100 and B plus 100, that means this system failure causes inconsistent database state, because we have only two consistent states in our example. Okay? So again, this is the same transaction. If the transaction executes correctly, it's going to transfer one consistent state to another consistent state. If not, system failure might be happening here. I put this one here for the reason after you update the value of A. Okay? So in this case, what happened? You start from A and B. This is the first consistent state. And after you execute this transaction, remember, you didn't finish all the instructions for this transaction. So in this case, what happened here? You see that the system failed. After you write A, so C, you didn't execute this one. You start from A and B, and you end up with A minus 100 and B. Do you have this consistent state? No, it's not consistent state. So that means if this one is not one of the consistent state that we have, have after execute this transaction, that means this is going to be inconsistent state. So there's something wrong here. So we need to make sure how can we recover this one. We're going to see how to deal with this. Okay? How concurrent execution? You know, when you talk about the concurrency execution, that means we have a multiple transaction that must be executed at the same time. So in this case, we're going to see this one next week when you talk about concurrency control. That means you see in this case we have a schedule, and we have you try to have interleaving operation that belongs to different transactions and going to be executed at the same time, simultaneously. Okay? So here we assume that we have two transactions. Each of them, for example, has one task. The first transaction is going to, for example, deposit $1 in account A. And the second transaction is going to deposit $2 in account A. Okay? So both of them are different. So let's do this one. The possible consistent state we have to, we have two consistent states. We start from A and we end up with A plus 3. Yeah, actually, it's all going to be this initial one and this is the new one. Okay, so regardless with the order of execution, this transaction, this is what we call the sequential, execution. So in this case, you execute the transaction 1, take the value of A, and add A plus 1. So this one is going to cause A plus 1. Then after that, I'm going to execute the transaction 2. So it's going to cause A plus 3. Or if you reverse the order, both, regardless of the order of transactions, is going to execute T1 and T2. I didn't execute this one, concurrently. I execute this one at a time. Remember, each transaction, if you execute completely, it's going to do what? Move or transfer the database from one initial state or consistent state to another consistent state. So this one is going to A plus 1. Then after that, after execute T2, it's going to produce another consistent state, A plus 3. If you reverse the order of transaction, both of them start on A and A plus 3. So you know what's the consistent state. Either A and you end up with A plus 3. Okay, so let's see how can we concurrent execution of these transactions. And again, the concurrent execution, as I mentioned, is going to be to come up with a schedule or interleaving operation here. Yeah, it depends on the data that we have here. So again, when you said consistent state as an example, as we said here, the initial consistent state is A, okay? After you execute the whole transaction, the transaction is going to transfer the consistent state from one consistent state to another consistent state. And we assume that or define the consistent state as what? This means all the database states or elements or database states is gonna do what? It's gonna satisfy all the constraints that we have or that you enforce in the database. For example, you can say, for example, one consistent state or consistent state that we have that assume the data is gonna store, let's say, the bank information. And you can define your consistent state here, for example, all the balance at the end of the day must equal $1 million, for example, if you perform a transaction within this, within the bank. Okay? So example, if you transfer $100 from account A and B, at the end of the day, must be the balance must be equal $1 million. If there's any failure or anything happen in the middle during the transaction from between A and B, so at the end up, when you check your consistent state, you see that you're not going to reach $100 million because it's going to minus the money that you deduct from A and you didn't manage to deposit in B. Okay? So here, consider the following concurrent execution. Good. So here, assume that we have, as I mentioned, both of them here. I'm not gonna, and by the way here, for the assumption, we assume that the transaction is correct. There is failure free. There is no bugs in the transaction. That means if you start with one consistent state, if you execute the whole transaction, this one is gonna transfer from one consistent state to another consistent state. Okay, so now this is, we have two different transactions and we try to execute both of them concurrently at the same time. That means we're gonna concurrent execution. That means we're gonna build one schedule and it's gonna mix these operations from two transactions. So this is assume this is one schedule. We're gonna talk about this one more details next time when we talk about the concurrency control. But this is assume that this is one transaction, or this one the plan in order to concurrent execution both transactions. So here, what does that mean? We start read A from transaction one is gonna read X. And remember, when you concurrent transactions, that means we have multiple transactions trying to access the same piece of information or the same record. We need to handle this one. Just I want you, there is an error that's going to happen here. So here, what happened? The transaction one access, what's the current value of A, and assume the value of A equal 10. So here, if they ask you for example, if the initial value of A equal 10, what is the consistent state after we execute the post transaction? It must be equal 13. Yeah, because you take the count A 10 after execute T1 and after that T2 or T2 after that T1, the result must be equal 13. Yeah, so here the transaction A gets the value of A, and then after that the transaction T2 is get access with the value of A. So both of them, they have the value of A equal 10 here and 10 here. Then after that, what happened here? The transaction one is going to add 1 plus 1 to the current value of A. The current value of A is equal 10 plus 1 equal 11 here for the T1. What's the current value of A or the local value of A at the transaction 2 here? He got the value 10, and here add 10 plus 2 equal 12. So A equal 11 at the transaction 1 and A equal 12 at the transaction 2. Either which one is going to write the data first? So for example, assume the T1 is going to write the current value. So this one is going to write the current value 11, A is going to equal 11. Then this one, transaction that is going to update the value of A after the first transaction, update the value. So override the current value of A with the writes 12. So we end up with what? We start with A and end up with A plus 2. Do we have this consistent state? No, it is not. We didn't define it. It must be A plus 3 in our case. So in this case, we end up that we have, the cause a problem here in this case. In other words, we lost the update in this case. So we need to deal with this situation. How can we deal with this one? We're going to see how can we use the concurrency control in order to not allow us to do that. Actually, you are familiar with this one. You are familiar about the locking, yeah? And you know that if you try to access data multiple transaction, multiple thread, you need to lock the data. For example, if you try to update the data. After you finish working with the data, you can unlock this data. We're going to see how can you perform this one locking, or maybe you can use the timestamp in this case. So, as assumption, we assume the data is going to be, the initial state is going to be consistent state, and the transaction is going to transform the database into another consistent state, F. There is no system failure. We don't have any system failures. So this means when you execute the transaction, it's going to be executed completely without interruption. And also, there is no other transaction executing in the database system. It looks like you are working by yourself. You are the only transaction that works by yourself in this case. Okay. Back to the transactions. So again, we said the transaction is the set of instructions, or I mean the operation is going to be operated in order to execute the query. Yeah, we can define this one as the smallest of the unit of execution in this case. When you say unit of execution of the database system operation, that means mainly it's gonna the operation then we are concerned here when the transaction is gonna update the data. And since the problem here to update the data, this is the most main concern for us. When you say the transaction is the unit or the smallest unit of the execution, that means this unit is indivisible. You cannot break it down. In other words, the transaction either going to be executed completely or nothing from the transaction that's executed. You cannot say, okay, I'm going to execute only, for example, partial transactions, or partial part of the transaction going to be executed. This is not allowed. So the transaction is going to be like atomic unit. That we either execute all the instructions that relate to this transaction or not at all, which makes sense. You see that the transaction, for example, transfer account data from A to B. If you partially execute this one, definitely this one is going to cause inconsistency. So we are trying to avoid that, to try to say you cannot do this one. So the transaction, you have to find a way in order to either execute the entire transaction or not at all, or nothing. So it looks like when you say nothing, it looks like we never saw this transaction. And I mean, how can we use a transaction, I mean, in, let's say, an application, for example, the database system today? So generally speaking, the SQL standard, you know that how can you use a transaction, yeah? So it looks, I mean, every transaction you can using start with the begin command when you write this one, and at the end you say, for example, this is the begin of the transaction, and you're going to list all the set of SQL or SQL query that we have. For example, update, modify, insert, and etc. Then after that, you can say commit the transaction or abort the transaction. Yeah. So if the user said, I need to commit the transaction, what does that mean here? This is one interesting thing. Generally speaking, we know that if that committed transaction, we know for sure that 100% the database is going to do what? It's going to save all the change that made by the transaction. Actually, in reality, not the case. It depends on the database management system at that time. Because the database management system, maybe because they said, oh, we do have a problem with this transaction. I need to abort this guy somehow. So we cannot guarantee. So that means in most of the cases, I mean, when you say commit, the database is going to make the change or make sure that, for example, the transaction, all the change that has been made by this transaction is going to be stored in the database or reflects the change of the database. It's going to be persist. And sometimes the database management system can decide, say, no, I need to abort this one. Why? Because, I mean, maybe this transaction, for example, maybe cause a problem. Or maybe we have a deadlock with another transaction at one point. So we need to abort this one. Okay, we're going to get back to this one here. If the user said abort, this means you have to undo whatever this transaction did. And the user, he can say that, yeah? And maybe someone wondering why we need to abort my transactions. It might be the case, for example, you do some computations, for example. Remember, the transaction got a set of operations. For example, read the data, modify the data, update, insert, and etc., and get data from the user, modify it, etc. Maybe the user give you like invalid data at the end or something. Maybe this one's going to cause a problem. So in this case, you need to abort your transactions. Okay? And again, the abort is either going to be by the user itself, or the one that's got to by transaction itself, or maybe it's going to be caused by the database system if the database system knows so that, oh, execute this transaction maybe cause a problem, or you are not allowed to do this transaction or this operation, and etc. Or maybe there's a deadlock in this case. Okay, so this is just an example. I'm going to tell you, all right, for example, in my case, begin, let's say, transaction or commit. Oh, by the way, if you are familiar with, let's say Postgres, I think so Postgres use rollback in this case, not abort. So either it's going to be abort or rollback. Okay, both of them are the same. So I'm just talking about the standards in databases, SQL, I mean. So here begin a transaction, and you're right, all the operation going to perform here. Then at the end, you can't tell whether it's going to be commit or not. And you can think about this one, for example, you give the user a chance at the end. Are you sure you want to change, make the change to make sure to make the change to your bank account or etc.? If you said yes, commit. If you said no, after you do perform the operation, you're going to say no, you can abort. And this is, I mean, either gonna begin transaction or abort. In most cases, that means will be executed. But maybe if you say the commit, all the operation gonna be executed, all the change is gonna be reflected change, unless the database management system gonna decide something else. You said, oh no, you are not. Oh, I know you said commit, but I cannot do it. Okay, for many reasons. If you have begin transaction, perform, changed, update, insert, etc., then after that, if you set abort, that means whatever you did here, it's gonna be is not gonna be executed. Okay, that's why none of these operations gonna between this part is gonna be has been executed. Good. So we talk about let's say transactions. And we said that, for example, we need to achieve, for example, we talk about the recovery control, mechanism, we said the recovery mechanism must achieve the atomicity and consistency and also the durability of the data. Just doesn't hurt if we remind you with the asset properties here, with the correctness criteria that we have for any transactions. So you are familiar with this one. Hopefully you still remember that. So the atomicity, that means in this case, you can say that simply that all the action in the transaction is going to be happen or none happen at all. Yeah, remember we said the transaction are like atomic units. That means either you're going to execute all the the commands that within this transaction, all the operation that listed within this transaction, or not at all. That means either you're going to execute the entire transaction or none. Okay. Consistency here, generally speaking, we can say, it's like correctness of the database. So that means if you execute the transaction, and remember that we start on the initial consistent state, that's the state that is going to satisfy all the constraints that we're going to enforce with this database. And if we execute the entire transactions by itself, for example, that means it's going to preserve the database, it's going to remove or preserve the consistency of the database. In other words, if each transaction is consistent, okay, and the database start or the initial value that was consistent, that means then it's going to end up that we have a consistent state. Isolation, that one interesting thing here, that means it looks like the database management system is going to give you the illusion that regardless that we have multiple transactions going to execute at the same time or simultaneously, I'm going to give you that illusion that you are the only transaction going to work by itself. And we're going to see this one, how to do this one, mainly using the concurrency controls. So in other words, it's going to look like you have an illusion that this transaction runs by itself. Okay? Durability, that means after you change, after the transaction finishes, commit, the transaction modifies the database or makes some change. Yeah, we need to make sure that these changes are going to be what persists. That's be durable. It's going to be stay in the system. In other words, it's going to be permanent. That means if you turn on your computer or start your computer or come back to your computer, you're going to see that whatever this transaction made the change must be persist, must be permanent, must be stay in the system. Okay. And the interesting thing here, even if there is system failure, we need to make sure that the modification of transactions are never lost. Remember, I'm talking about the transaction that finish or completes successfully, is committed. We need to make sure, even if there's an error happen, or failure happen in the system, we need to make sure that whatever the change made by this transaction must be reflected as this, must be there, must be permanent. Now the interesting part. How can I implement transaction? Or in other words, what kind of technique that I can use in order to allow me in order to perform this kind of transactions? Okay? The first one that we're going to talk about here, okay? So we're going to talk about the logging. We are familiar with this one. This is one technique we're going to use in order to make sure how can we achieve or make the database going to achieve what's called the atomicity and durability of the database. And synchronization, for example, you can use in locking, or we're going to see using timestamp that in order to implement the isolation property. Remember, the isolation, that means to give you illusion that you are the only transaction that's executed or run by itself. Regardless, there's another transaction at the same time, which is what we're looking for. That's what we're going to try to achieve that. So it looks like the concurrency control is going to try to achieve the isolation, and they say the recovery mechanism that or control is going to try, achieve or ensure atomicity, durability, and consistency. In other words, yeah. We assume the consistent property in most of the case based on the transaction. we do have two different consistency, one of them for the database, another one for the transaction. We're not going to cover this one. We assume that the transaction works fine. There is no bug in the transaction itself. So the set of operation going to be listed within this transaction is correct. Yeah, there is no bug in the transaction. So that means if you execute these transactions completely or successfully, this one is going to transfer the database from one consistent state to another consistent state. In other words, when you execute the transaction completely, this one we assume that this never gonna cause the database database state is gonna be end up with inconsistent state. Okay. So now, when you talk about the logging here, what do you mean by the logging file here? So it looks like what I'm gonna do here within execution, in the normal execution here, I need to add or create or come up with some extra piece of information. I need to store this one somehow in a way that is going to help me in order to recover in case any failure happens in the system. So I mean, again, during the normal execution of any transaction, for example, remember the transaction that transfer $100 from account A to B, I need to have another piece of information going to be record let's say the steps going to be made by this transaction. The transaction did this one. The transaction moved this one. The transaction modified the value of, for example, A. And I need to make sure that maybe keep tracking for the old value of A before the change made. And maybe you need to keep tracking, for example, the new value of A, and etc. We're going to see this one. How can you build this one? In other words, we try to come up with something called logging file, with a logging file that contains a sequence or set of instructions or commands or entries or records that allow us in order to recover from the failure if that happened. Okay? So the log file is append only. That means you just add the special file that contains, the log records. A special is a normal file. Is you have a records, and we call these records as a log records. So we need to take a look what the structure of log record, what these log record doing here is going to record. As a tuple in the log file, which contains information required or needed or allow us in order to recover from any failures that happen in the transaction. And we're gonna see that we do have two different types of log records. We're gonna study this one by one with the time, okay? One log record is gonna allow me to undo. Remember what to undo, this means roll back whatever the transaction did in the system. Another type of record is gonna be a log file that allow us in order to redo the effect or whatever the transaction did. Okay? What's the format it's gonna be here? It's gonna contains this information. So it's gonna be the transaction ID, which the transaction is gonna execute here, or what kind of, we have many transactions. Remember, you are not alone. The transaction is not alone. We do have many transactions. So the transaction ID, what kind of action transaction did, what the actual transaction did in the system. Generally speaking, reading and writing, something like this. We're gonna see what kind of action next slide, okay, in general. So then after that, this transaction performed this action over what? Which database elements here? So in this case, maybe A, B, C, or whatever. Then here, we are going to store the value. So it depends what kind of value. So it depends what kind of, log file we're gonna do here. This value, maybe it's gonna be the old value of A, or this database element, or the previous value, or the new value, or both of them. It's gonna be the old value and the new value. Because what we're doing here, for example, I'm interested for the update when you write or modify the element A, for example. I need to keep tracking the old value, or maybe I need to keep tracking the new value, or both of them. It's going to be stored here. Okay? This information it's going to be creating what it's going to, whatever you're doing in your transaction, we're going to see that we have different way how to build this log file. This is going to be created must be in the main memory, definitely. All the information you have to create one block, and this block is gonna start. You are going to, for example, store the log record outside this block in the main memory. Then after that, you have to fetch, or you have to store this one or reflect the change of the disk. You need to make sure that you have this information that must be stored in the disk. So in any emergency situation, for example, the system crash, etc., what's the first thing the database system do is going to go back to the data to the disk, retrieve the log record, and then after that try to recover from the errors. Okay. Sometimes the log record is going to be forced into disk. That means I'm not going to wait until the disk is going to be, the block in the main memory is going to be full. So sometimes it's gonna depends on the recovery mechanism. We're gonna see that in a few slides later. That means I'm gonna say if the transaction performs specific operation, now you have to store whatever reflect the change that you find in the main memory. The local record that's stored in the main memory must be in the disk. Make sure there. So we call this one gonna be false in the disk. So let's first start. We have many actions. What kind of operation? What kind of action that we can do here? So in order to understand this one, let's assume that let me give you the situation here. We have actually 3 spaces, okay, or 3 memory spaces we work with. The first one we know that is let's call this one the disk space. That means the data is going to be stored in the hard disk, and we have the main memory, which is the buffer pool, yeah. Or let's say memory. Then we have another space here. We call this one here, the transaction or the local address space, or I'm gonna call this one transaction space. Okay. So what does it mean here? So it looks like we have different space. In order to work with data, you need to work in the 3 different spaces here. So the database, this means in the transaction, for example, you try to access any piece of information. This information must be reside in the main memory. If it's not, that means you have to fetch the block that contains this database elements from the disk space, from the disk into the main memory, which makes sense. We cannot operate directly on the disk, so that means whatever you need to operate must be in the main memory or the buffer. And you know that for every transaction or request, it's gonna have its own local memory space in order to perform some operation. Okay. We do have 3 different operations here. Okay. Many operations. The first one, input. The second one, output. And the third one, we call them read the data element. And the fourth one, write the database element. Okay, let's do this one by one. What's the input here? The input, that means if, for example, if you said, let me write the operation with different color. If you said, for example, input X. What does it mean here? That means here we need to copy the disk that contains the database element to the buffer. So here it looks like, let me have a small thing here, this one block, and inside this block is gonna contain the database element. Yeah, and remember the unit that we're gonna use, we said it's gonna be block. For example, if you have X1 database element, we'll get 1 block at a time. And we assume the database element is going to fit 1 block. If not, that means you have to perform multiple disk input output operation in order to fetch all the information. But for simplicity, the database element, 1 block, 1 disk input output operation is enough in order to retrieve the database element to the disk. So again, when you perform the input X here, input X, that means please transfer or copy the database element block that contains the database element to the block, to the disk, to the main memory. So I'm going to copy this one here. And now we're going to have, let's say, let's write this one here. The X is going to be, okay? That's the input operation. We do have another operation. We call this one read XT. So read XT is going to be initiated by the transaction manager. For example, I need the transaction set, I need the value of X, and I need to store this one into the local variable T. That's the meaning here. So what we're going to do in this case, the transaction, I'm going to have, let's say, different color. So the transaction here, it has, let's say, variable T here. This one, I'm going to say, I need what's the value of X, something like this. How can you do this one? The transaction I perform like, I need to read the value of X. So that means take the value from here, and I need to store the value from X here to the space, to the local space. What if the block that contains the database element X wasn't exist in the main memory at that time? So in this case, if it's not exist, this means the buffer manager is going to do what? It's going to issue input out X in order to fetch the disk block that contains a database element from the disk space in the main memory. So again, if the transaction or local space you need, for example, X to the database element, is going to issue read X. Read X, that means read the blocks or the data, copy the database element to the transaction local, space or variable T. If the block that contains the database element X wasn't available in the main memory, that means automatically the buffer manager is going to do what? It's going to execute what is called the input X somehow. It's going to take the block that contains the database management system, the database element X from the disk space must be resides in the main memory. Clear? You perform some operation, whatever. Then after that, you need to do what? You need to update the database element. What does that mean here? The transaction is going to read the database element X, perform some operation. Then after that, it's going to perform the operation over the local element, variable T. For example, X plus 1 or multiply 1, do any operation. Then after that, I need to reflect the change to the disk because I need to write the data in the disk. So the transaction can use what's called here operation. We call this one, I will write this one here. We call this one write the database element T X in the disk here. Okay, so what does that mean here? Write whatever you have in the local variable T in the block that or the database element X. In other words, copy the value of the transaction variable T and store this one to the database element. So when you do copy this one, that means this one is gonna be perform the operation here. Okay. What if again the disk or the block that contains the database element X wasn't available at the main memory at that time? You know that the memory has, the buffer pool has a limited space. Sometimes it's going to get rid of this block. Yeah. So now I need to update the data in the main memory. So what we're going to do here in this case, I have to perform the input X in order to make sure the fetch or copy the block that contains the database elements must be reside in the memory. So again, the transaction here, the transaction can read the data from the main memory. If it's not available, the disk, it must be issued input X by the buffer pool in order to make a buffer manager in order to fetch the block that contains the database element to the disk, to the main memory. After I perform some operation, the transaction is going to write or update the database element X. So it's going to do what? Copy whatever has a local element T into the database element X. So when you perform this operation, can you do this one directly in the disk? You cannot. You have to operate this one. The block that contains the database element must be resides in the disk, in the main memory. So in this case, write the value here. If it's not exist or wasn't available, that means the database, the buffer manager is going to issue input X. Now, after you've done this one, how the data is going to be written here? So the buffer manager is going to do what? It's going to do another operation. We call this one output here. What's the output here? That means you have to reflect the change to the disk using the output operation. So here's going to be output X. What's the output X? That means it's going to do what here? It's going to couple the buffer that contains the database element and store this one into the disk. Now I'm gonna update the value of X. So again, this is the operation gonna be performed by any transaction. The transaction gonna read the database element is going to read this one, copy this one from the main memory or the buffer memory into the local space. It's going to issue read X and T. That means copy the element TX and put it in the T, local variable T. If the block wasn't available in the main memory, that means the buffer is going to do what? It's going to issue input X. That means take the block or fetch the block or copy the block that contains the database element X into the main memory. If the transaction tries to update any one's done from the operation about this database element, it's going to try to update this one in the local memory. So it's copy from the local variable into the database element that's stored in the main memory. If it wasn't available, we have to perform input X, which must be resides in the main memory. Then after that, you're gonna perform output X. That means output X is gonna be update, copy the the container or the input output of the block of the page that contains the database element to the disk. Okay. If we understand this one, that means the rest is gonna be easy. And all these operations are gonna be summarized here. Clear, guys? Okay. We assume, as you mentioned here, good. We assume that, for example, the database element is only one block. That means we never exceed the size. So if you fetch one block or one input-out operation is enough in order to fetch the database element. If the database element is larger than one block, that means you are going to perform more than one disk input-out operation in order to fetch the data or read the data. But for simplicity, we're gonna say it's enough. It can fit less than or equal one block. Read and write operations are issued by the transaction, and you see who's gonna read the data, the transaction. Who's going to update the data, the transaction. The input and output is gonna be issued by the buffer manager. The input take the data from the block from the disk and put it in the main memory or the buffer. Then after that, the output is gonna take whatever you have in the buffer. You have to reflect back or store this one in the disk. Sometimes the output can be initiated by the log manager. We're going to see this one later because we're going to come up with some, mechanism in order to allow us to undo or redo the operation. So the we're going to see sometimes we're going to say, now you have to output, you have to reflect the change in the disk. Right now, you have to enforce the system to do that. Okay, this is a simple example. So we have the database element, just show you this primitive operation, how it works. So you have a database element A equal 8, and the database, and we have two different database elements, A and B, both of them equal 8. And our constraint, for example, is saying A must be equal B in all consistent state. So that means whatever you make a change in the A or the B, at the end, after you execute this transaction, must be they are equal. Okay, this is our condition. So we have a transaction, and the transaction is going to do two steps. It's going to multiply the database element A by 2 and the database element by 2. So that means if you start with 8, the result is going to be 16 in A and B. Yeah? Okay, and this is the transaction. You read the data in the local variable T, read from the database element, and store the information local variable T. Then now locally you can operate over this, multiply, modify, whatever. Then after that, I need to update the value of A. Then after that, read the value of B, multiply by 2, then update the value of B. And you can reverse the order, it's fine. You can start reading B and A. So in this case, when you execute this one, we start A equal B, and we end up with A equal B, okay? So we're gonna see, in addition, when you perform right in the data, you see that the data buffer manager is gonna execute output step in order to make sure that this data reflects the change made by over the on this database element must be reflected to the disk. So let's be happy. This is one interesting thing, okay? So here, just I need from you to understand what's going on here. So this, just show you the steps of the transactions and how it's going to be their effect on the memory and the disk. Remember, we say that we have the memory space. We have the disk space. This case, the data is going to be in the hard disk. For example, you have a disk A and B. That means what the value of A or database element at the disk was 8, and this is going to be 8 at the beginning. This initial space value. This is going to be the buffer pool or the main memory space. We have the memory A and B just to specify that what's the value of A and the memory and what's the value of B at the memory. Of course, here is going to be block that contains the database element A, and this another block maybe that contains the database element B. Okay, this is what the current value of the local variable we're going to use in transaction, and this is what kind of action. So it looks like here, this is the memory, the main memory space, and this column is going to represent, they say the main memory space, and this column is going to represent whatever happened at the transaction side of the transaction space. So here we did nothing. This is the count space. Then when you read A and T, what happened here? You're going to do what? The data wasn't here, yeah? So what you're going to do here, the system, the buffer manager is going to do input X. Input A. That means fetch whatever the data block that contains the database element A and store this one in the main memory. So the memory A is going to be equal 8. Yeah, when you do read, this means and copy the value of the local variable. Okay. Then the next step, what? We're gonna perform the local operation. For example, multiply T by 2. So I change only T here, 16. Did you change A? No, in the memory, no. How can you change this one? When you say write A and T. When you write A and the T, what does it mean? That means you have, if the data is going to exist in the main memory, so that means you have to update this one with the local variable. So let's copy the new value here in the A. So here the T is 16. I'm going to update this one in memory. And here note C. Did you change anything here? No, in the disk. Right, this means from the transaction space into the main memory space of the buffer space. Do the same operation for the B. B is equal 8. And still I didn't touch this value of A, there's just a work in the B. When you fetch this one, the value current value B is going to take the disk, multiply by 2, then after that update whatever you have in the T here, so both of them have 16. And this stage, did this change anything in the disk? No, everything the change happened in the local transaction space and the local space for the transaction and also the main memory. Now when you say output A, what does that mean output A? Copy the block that contains the database element A into the disk. So that means when I say output A, I take whatever I have in the main memory and I'm going to update the value of the disk. Output B, the same thing, is going to perform the operation. So at this time here, when you finish here, you see that you start from 8 and 8, and the end you end up with 16 equals 16. So still the value of A equal the value of B. So to achieve our consistency that we assume in this transaction. We have, it's worth mentioning here that remember we said sometimes when you execute your transactions, Okay, a transaction. Maybe it's going to be in the middle of the execution of that transaction. The database system or element is going to be, the database system or state is going to be inconsistent. It's okay. You see that in this stage, if you check the value of A and B, you see that they are not equal in this one, because I didn't finish the transaction. Now, after you finish the transaction, you can say commit here at this stage. You say, oh yes, it's fine. Okay. So we do have a transaction manager, and the transaction manager is going to do something. It's going to help us in order to recover from any errors. So the transaction manager is defined as a piece of software or as a software component in the database management system that implement the behavior of the transaction. What do you mean the behavior of the transaction? It looks like it's going to record whatever the transaction doing. I can record this one. And also it's going to make sure that later you're going to make sure that the concurrency execution transaction doesn't interfere with each other in order to make sure that the database is going to be resolved. Make sure that the database must end up with a consistent state. We're going to see this one next part when we talk about the concurrency control. We're interested just here what the task that the transaction manager is going to do in order to achieve or make sure that, we can recover from any errors. Okay, so the function is going to perform. Most important thing, we call this one, all right, who's gonna, remember we said we're gonna have a log record, yeah, or log file that's gonna contains the log record, is gonna have whatever action they made by the transaction. Who's responsible? Who's the unit is gonna be responsible to update, to write, or create this records? Entry, log records. This is performed by the transaction manager. So the transaction manager is gonna create this one. Remember, all these record log is gonna be stored in the main memory. So if the transaction started, so the buffer, the transaction manager is going to do what? It's going to add this log entry. This is the structure of the log entry. Now we're going to take a format. It's going to say start T. That means the transaction T is started here from this point. So it's going to write this one into the log file. Okay? Then if the transaction perform reading, we're interested just in the read and the write. Do we are interested in what the transaction do in the middle? I don't care. The most important thing, I need to make sure that the transaction read the piece of information or the database element. Then after that, the transaction try to modify this database element, because I'm interested in the most important piece of information, what's the current value of the database element A, and what's the new value, or what the transaction did with this value. Yeah. So here, if any transaction start, the transaction manager is gonna add this record to the log entry file. If the transaction read the data, it's gonna read A or whatever, so it's gonna read whatever element is gonna be read by this transaction must be writing in the log file or log entry. If the database, for example, the transaction perform writing X, T or whatever, the transaction is gonna write something to the log entry or the log file, and the transaction. No, this is we just here we don't care. We have only one transaction. Yeah, we're gonna read this one. Yeah, right now this recovery. From the failure. Here we assume that we have the transaction work by itself. Later, when you talk about the concurrency control, then we're gonna see that we have a multiple transaction gonna execute. That's a different story. Yeah. It might be have a different transactions, yeah, but in this case, we worry about that. How can we recover if one transaction fail or the system crash? Later, when you talk about the concurrency control, we're going to see how can we deal with the situation. We have interleaving, concurrency control, concurrent execution of transaction. How can we recover? Because the goal there in the concurrency control, you need to achieve the isolation. Here, the goal is just to make sure that after we execute this transaction, the database must be in the consistent state. We achieve the atomicity, we achieve the consistency and durability. That means, yeah. Okay? So when you end the transaction, you're going to be commit T or abort T. Yeah? So let's see. This is the example that we have. We are familiar what happened here, yeah? Okay? Just I want to ignore this part for a while, okay, for the error that's happened here. So we do have a problem here. So we have this transaction. Assume that at the beginning we don't have this errors. This is what we did here. Read A, modify, multiply A by 2, then B, multiply by 2, then update the data in the memory, then the system gonna update this one to the disk. Yeah, good. So here, what we're gonna do here. What if there is something happening in the middle here? What happened here in the system? We start with the consistent state, and we end up with inconsistent state. Do we finish this transaction? No, we didn't. So in this case, we need to make sure that we come up with the way that we call this one the atomicity. We need to ensure the atomicity in this case, that means either execute the entire transaction or none at all. Okay? So it looks like we have to desire state after any system crash or any system failure. I will talk about the system failure, okay? So in this case, either I need to have two things. Either the change that made by the committed transaction. What do you mean by committed transaction? The transaction as executed completely. Yeah? The entire, instruction completely. Must be reflected in the disk. Whatever change made by completed transaction must be permanent in the disk. And we need to have another state, another desirable state after I perform the recovery from the cache. Whatever change made by unfinished transactions are not reflected in the disk. That means we need to make sure that unfinished transaction after recovery, it looks like we never run this transaction before. So here in after crash, we need to do two things. We need to undo the change that made by unfinished transactions, okay? And we need to redo the change made by committed transaction in order to make sure that all the change made by this committed transaction are reflected to the disk. So we need to store, in this case, some additional information or data in order to help us or allow us in order to do undo and redo. So we need to know the following in the logging and recovery here. We need to make sure in order to make sure this information that in order to undo or redo, I need to make sure that what kind of information has been executed. And also, which information that reflected in the disk. In other words, you know the transaction is going to read the data from whatever A and B before some computation, then after that sometimes it's going to write the data or update the data at the disk. So I need to find a way what kind of information that the transaction did so far, or up before the crash, or until the moment of the crash, and also what the operation that's going to be reflected in the disk. When it reflected in the disk, that means the transaction managed to write or update the data in the main memory, and the buffer, let's say manager, execute what is called the output, so reflects the change in the disk. Okay. So in this case, what we are gonna do here, we need to have like an extra piece of information in order to allow us in order to cover up in this house. So we call this one log upfront. What is to be done here. So now we're gonna take a look what I'm gonna discuss some approaches that allow us for the logging. How can we add or create this extra piece of information that allow me in order to recover from any errors? So just one slide here. So here, generally speaking, we have two different logging techniques. One is the name of this one, undo logging. The other one, redo logging, and the third one, undo, redo together, which is the one you're gonna end up here. The first one, undo logging, that means there's a log file that contains a log record. We're gonna see how can we create these log records in order to allow me to do what? In order to enable us to undo. When you say undo, that means roll back whatever the effect has done by the uncommitted transaction or uncompleted transaction. So the transaction never finished. Okay? We have another redo logging. We're going to see how can we build this log file, which allow us in order to what? It's going to contain the log record that in the way that allow us to enable in order to redo. Remember, we said we need to do that. Two things, undo uncommitted, action done by uncommitted transaction. We can do this one using undo logging, or redo the action or the change made by committed transaction in order to make sure. We're going to see later someone will say, why you need to redo the action done or change made by transaction? Because we are not sure whether the change reflected the disk or not. Sometimes you're going to see that when the transaction said, write or update the value of X. The system, maybe we made the change only in the main memory, but we cannot guarantee that this change has been made to the disk. Yeah? So that's why we need to redo. Undo and redo, this has two things. So here I'm going to build my logging file. It's going in order to allow me to do two things. And do whatever, the change made by incompleted transaction, and redo the change made by completed transaction. So it looks like this one is going to do the both. Function provide by two different, logging techniques. Okay, let's take a look at the first one, how to build this one, how we use this one in order to recover from the crash. Then after that, take to the second log file, how can we build this one, how can we, use it in order to recover from the crash. So the question here we need to think about first how the log file is written. Remember, all the we can divide the log file into two parts. Okay, the first part is going to be in the main memory, and the second part is going to be stored on the disk. So this assumes that we have a block that contains, let's say, the log file is going to be in the disk, and we have another one log file that is going to be in the main memory. So every time you have to fetch, a copy from the block from the disk to the main memory, start fill the log file, the log entry here for the log file. When this block is full, it's gonna do what you need to write this one back to the disk. So at a specific moment of time, we have like two versions or two copies from the log file. One that resides in the main memory, in the disk, and the other one gonna reside in the main memory. We need to figure out when we need to decide, for example, at what moment we need to, let's say, write back the block that contains the log file that resides in the main memory to the disk. Okay, the simple operation or simple way to rule if the log, say the block is full, then in this case we have to write it back to the disk. And we're gonna see later that we have different, logging algorithms, okay, logging techniques. Each of them, they're gonna have a specific rule to decide when we're gonna, do this operation. Whatever you have the log entries that's stored in the memory, when we need to store this one into the file and back to the disk. Okay, so how can we before this one? We're going to take a look first the log writing rules, which for each log file techniques, they have like a number of log writing rules. That means when you need to reflect or store or whatever, take whatever you have in the log entry there to store in the main memory, and you need to store this information in the disk. When you're going to reflect this one to the disk. We call this one again the log file writing rules, which specifies, specific ordering of write operation to the disk. You have to follow these rules for every, depends, of course, on what log file technique or log technique you're gonna use in order to make sure that you can write the information or you're gonna find the information that you need in order to recover from the cache. We have what is called the log flush, operation, which you're gonna see that it depends on the log writing rules. For example, let's give you a simple rule. For example, when you try to modify any database element on the disk, you cannot do this one until you do, let's say, flush whatever the log file entry to the disk. You have to make sure that we have the structure that modify the database element must be stored on the disk before you make change on the database element. So you're gonna see that it depends on the logging technique. You're gonna see each of them, they have specific logging right when you need to flash or whatever, store whatever in the the log entry that's stored in the main memory to the disk. So in this case, we're gonna use what is called the log flush, which is gonna be like an operation or like command. It's going to enforce, the buffer manager in order to reflect or store whatever you have in the disk and the main memory of the blocks that contains the log entry. That the main memory must be stored in the disk. So let's take a look to undo logging, which is the first one. The undo logging now, we're going to take a look. How can you build the undo logging file that allow us in order to undo uncompleted transactions. So at the beginning, we're going to assume the log file is append only. This means you cannot delete any information. Whatever you have stored in the log file is going to be reside forever. Then later we're going to see that how can we trunk this one, how can we reduce the size, okay? And remember, when you say the logging here is going, file is going to only allow you in order to use to roll back the change made by the uncommitted transactions. So let's see what kind of operation or what kind of, the record we need to store in the log file. We're going to have a start, okay, which indicates that the transaction T has started, commit or abort, which this means whether it's going to decide whether the transaction is completed or let's say aborted for any reason. It's worth mentioning here that abort means that the transaction has completed but unsuccessfully. That means something wrong with the transaction. That means we decide to abort, to stop, whatever, cancel the operation done by this transaction. This is a very important entry, log entry here. We have, transaction X means modify the database element X, and the V used to be the old value of the previous value of X. We need to keep tracking for the old value or the previous value. And it makes sense here, because what we try to do here, we need to redo. We're gonna, as I mentioned, we need to add extra piece of information that allow us to know that to redo the change made by an incomplete transaction. So in order to reverse, but try to find, find the most consistent state for the database management system, database system. So, the database of state, that means you need to do what? You need to keep tracking, for the previous value of the data, every single database management, database element that modified by specific transaction. And how can we generate it? This log entry is going to be generated when the transaction manager tries to do what? Write the value of X. So here, for example, you have a transaction. For the transaction, for example, said, let me write here, write the value of X, okay? So when you issue this one they'll do what? We have X in the main memory, and this block that contains X, we need to update the value of X, yeah? The main memory, here. When you issue this one, so the transaction manager is going to write here for the log file, new command, they say transaction X, modify the database element X, and they say the previous value of X was 5. Keep holding the previous value of X. So later, if you have this entry, and they try to redo the change made by this uncommitted transaction, I can reverse all. I can make the value of X, the old one was 5, so now store the value of 5 in the database element. You're gonna see an example here. So now we have some rules. So we do what? We have like a log file, so resides in the main memory, and we have some entries. And these entries are going to be in this format: start, commit, abort, and we have modified some database elements. All this information first is going to be stored in the main memory. Now we need to decide when you need to reflect the change to the disk. In other words, we need to make sure how can we, flush the contents of the log file that resides in memory. We need to make sure that it's going to be stored in the disk. The writing rule 1. So here for the undo logging, we do have 2 writing rules. We're going to decide when you need again to reflect, flush whatever the log entries that stored in memory into the disk. The rule 1, if the transaction manager tries to perform output X, and remember what do you mean by output X? That means you need to modify or reflect a change of the database element into disk. This new value must be stored at disk. So change the value of X to the disk. So the transaction manager must make sure that the log record entry that transaction X modified the database element X, and this is the old value V, must be what? Must be written to the disk. So that means this log entry must be resides in the disk, must be reflected in the disk in the log file before I'm going to modify the database element X, which makes sense, yeah. Because remember what we try to do here, we need to undo whatever changed by this transaction. That's why we need to make sure that you have this entry in the disk. Yeah. The rule number 2 here, if the transaction tries to write a commit log record to the disk, we're going to show you, the example that's before the transaction is done, and the transaction is going to write a commit T, and that commit T first is going to be written into the main memory. Then now the transaction manager asks, say, I want to write this one to the disk. Make sure that the commit transaction is done. I want to remember when we say write to the disk that I'm talking mainly about the rules, how we're going to control when we are going to store or reflect the log file from the main memory to the disk. So before I do the commit, I need to make sure that the transaction manager must write or update the change made by the transaction over every single database element here. Assume this transaction touch or modify X1 up to XK. That means before I write the commit to the T, that means before I, mark this transaction as a commit or completed successfully, I need to make sure that every single change made by this transaction must be reflected to the disk. How can you show this one? Modify the database element, or all the database element touched or modified by this transaction must be reflected change to the disk. And again, before you perform output, you need to make sure that you have this log entry must be written to the disk. Okay? And here, the reason behind this one, I need to make sure that here, in this case, remember the undo logging, what the goal of this log file is going to allow me to undo the change made by the incompleted transaction. Do you want to have, care about the change made by completed transaction in this case? No. Okay? So this is, the algorithm is gonna summarize the two rules. So here the transaction manager speaking is executed, let's say, an operation, depends what kind of operation, maybe read, maybe something like this, or output or commit or whatever. So the first, if the operation that the transaction manager tries to execute is output, and remember, what do you mean output? This means I want to reflect the change, or write the new value of x to the disk, change the x in the disk. This means you need to make sure what? I need to enforce that the rules that we're going to have right now. I need to enforce whatever do we have in the buffer pool, that all the log entries that stored in the buffer pool must be stored in the disk. This is going to ensure that the T and X and V must be written to the disk. Then after that now, okay, you have to perform output X. Remember last lecture we used to show you the flow between the disk and the main memory and the let's say the transaction local memory. We are going to use output X, and we have sometimes we're going to use input X and read and write, etc. Else, what if the operation commit? If the transaction manager tries to execute commit, that means I need to write the commit to the disk. This is a log entry. I need to make sure that all the change made by this database, let's say this transaction, must be updated or must be written to the disk. This means output whatever, every single database element. D, that means when you do output, that means you have to do in this way operation. If this output, they have to make sure that you have this log entry before modify the database element. D, must have this log entry T and D, and whatever the old value of the D must be written to the disk. Okay, then after that, flush the log the disk. Why I need to do this one? Because I don't want to wait until the buffer pool is going to decide that this is the time because the block is full. I need to, make sure the change made by or whatever the content of the block must be written to the disk. This looks like here, I'm going to enforce the buffer manager. Right now, you have to reflect or store whatever or write whatever you have in this block to the disk. If there's any other operation in this case, I'm not going to do anything here. Okay, so this just general summarize what we said right now. So the undo logging, we have two rules for every single action generated. Undo log record containing old value. This is the most important thing. Before X, whatever database element is modified to the disk, we need to make sure that we have, the log record that pertaining, to X must be to the disk. Within this case, T, X, the previous value of X must be written in the disk first. We call this one write ahead logging. So write ahead before make any change in the log file. Okay? Before commit is flushed to the log, that means all the write transaction must be reflected to the disk. That means we are going to perform or issue output with every single database element that touched or modified by this transaction. Let's have an example. So this is an example, okay? And generally speaking, in the example, something I'm going to give you like the log file here, or let's say that's stored in the main memory. In the disk, okay? It must be here. It's going to be here, okay? So we do have example. We're going to go through maybe 2 or 3 examples next section. So here we have an action. Remember that we divide this one in 3 parts. This is whatever we have in the disk here, whatever we have in the main memory, and whatever we have, let's say, in the the transaction locker here. I add only one part to the main memory here. We call this one the log file or log entry that's stored in the main memory. So in the disk at the beginning, we don't have anything for the log file or the log entry gets stored in the into the disk. When the transaction starts, so the transaction manager is going to write what? Start T into the log file that's stored in the main memory. So we have a one block, it's going to contain all the information, all the log entry for the log file. When the transaction before read, do we need to store anything? No, we are interested in, remember, they'll show you the operation that we need to have the log entry. Start, commit, import, and write. Yeah, these kind of operations you need to store. So the read is going to just perform, remember, read that means we have input, whatever we have on the disk, it's going to be stored in the main memory. So fetch 8, modify the value of A, for example. Now when you write A and T, what's going to happen here? Remember this, when you, to the transaction issue this command, so the transaction manager is going to write what? It's going to write this log entry in order to hold or keep tracking whatever this transaction did in, let's say, any database element, to say what is all that modification done by this transaction. So here we set the value of A is equal, let's say, modified to the 16 in the main memory. I don't write anything in the disk because I didn't issue anything in the, I didn't issue output X here. Yeah. So here in this case, I'm going to write TA and 8. This means this is the database of the transaction modify the value of database element, and the old value of A was 8. Did it change anything in the disk? No, I didn't issue output. Then in the same gallery, the database element B, modify this one in the main memory. Then still all the modification gonna be only in the main memory and the or let's say the transaction local memory. Then it's going to write this log entry here. Now, what if the database or the transaction manager issue output A? Remember what do you mean by output A? That means reflect the change that made in the disk. I mean the main memory, and write this one into the disk. That means I will take whatever the value, the new value that's stored for A in the main memory, and store this one here in the disk. Before you do this one, remember the first rule. You cannot modify or make change of the database element on the disk before you make sure that this entry or any or this log entry must be reflected to the disk. So in this case, what we're gonna do, I'm gonna use the flush log. When you say flush log, that means whatever you have in the main memory that belongs to the log file, store this one in the disk. Now in the disk, what we have in this case, we do have whatever here is going to be stored here. So now we have start T, and these log entry is going to be stored in the disk. Then now you can issue output A. That means now you can modify the database element A in the disk and the database element B in the disk. If you issue commit here. Before I do the commit, I need to make sure that I need to flush all the entry here. It's going to be in the disk. Now I need to make sure that all the output will be already before the output, modify the database element in the disk. And before I do this one, I need to make sure the log entry that captured this operation must be written in the disk. So this is what we have in the disk, in the log file. Again, when you start to do any action, our transactions, our transaction manager, whatever is everything is gonna be recorded in the main memory. Then the rules that we have is gonna specify the order when we need to flush whatever we have in the memory is gonna be reflected to the disk. And again, I'm just focused right now on the log entry, the log file, because we need to keep or do some set of action that allow us, or ensure the database management system can recover from the any failure. Clear? Any question, guys? Okay. So how can we, generally speaking, recover from this one? In other words, if I give you this piece of information, how could we use this one to recover from any errors or any crash? So here we need, in the undo logging, I don't care about, the log entry that belongs to the committed transactions, if it's the complete successful. Because what I'm trying to do here, I'm going to use this information in order to undo and committed transactions. And if we have all of them with committed transactions, that means I don't care about the committed transaction. So we define uncommitted transactions that any transaction that doesn't have a log record called commit. And also you can add a port, okay? If you have any transaction has a port with commit, that means we call this one is like a completed transaction in general. So therefore that if we found the commit T of any transaction here written in the disk in the log entry, that means it's like an evidence or proof that this transaction has completed. In other words, all the change made by this transaction are reflected in the disk. So in other words, since this log entry that you filled, the log techniques that you use here is undo, that means you don't care. You just ignore any committed transaction. You only focus on uncommitted transactions. That means any transaction that you have that doesn't have any commit entry stored in the log file. So we're going to use a recovery manager. So recovery managers again is a software similar to the transaction manager. It's a software component, the database management system, which is responsible in order to restoring the database into, let's say, the consistent state after system failure or crash. Okay. So here we need just to emphasize that the committed transaction must survive the system failure after the recovery, which makes sense because if I found the commit T based on the rules that we have, I cannot write the commit T in the disk until make sure that every single change, or I need to perform the output for every single database element that touched or modified by this transaction. I cannot do this one until make this one or the log entries are stored here. Yeah. So if you have a commit here, that means all the change made by the transaction is reflected to the disk. That means that's perfect. So even if there is a crash, you don't have a problem, because based on the rules that we have, all the changes are reflected to the disk. So this, remember the transaction, we mentioned that last time, that the transaction is going to do what? It's going to transform, the database system from, or the database, to say, from one consistent state into another consistent state if this transaction completely successfully finishes its work or job. So how can we use the undo logging in order to recover? So how can you use whatever have the log entry in order to recover from the crash? The first one, if you find commit, ignore this one. All the data entry or log entry that belongs to this transaction will be ignored because it's not going to be useful. Okay? So in order to perform recovery from the system failure using the undo log, I need to find what? I'm interested in only for uncommitted transaction. You need to identify them. How many uncommitted transactions you have? 5, 6, 100, 1 million, whatever. Okay? You have to list them. Then after that, you are going to do what? You're going to do in the reverse order, take a log, start from the end of the log entry that we have, log file, sorry, from the end, and go backwards up to the beginning. All the uncommitted, any action made by any uncommitted transaction, you have to reverse the action. In other words, for example, assume that this is a uncommitted transaction. We don't have a commit T here. For example, I start from here, this uncommitted, I start with the reverse order from the end to the beginning, and reverse all the modification made by this transaction. For example, this transaction modified the database element B with a new value. I don't care. When I have T, B, and 8, what I'm going to do here, I need to make sure that store the value of D to restore to the previous value 8. So in this case, I'm going to issue what is called, write P and the value of 8 in order to make sure the value is going to be stored here. So in this case, I need to output the value of P and restore the value of A as a new value, and etc. Then after that, mark the uncommitted transaction after you reverse or undoing whatever change or update made by this transaction. I need to mark the uncommitted transaction as aborted. And the reason behind this one, remember, we have the transaction, we said we have a rule for the atomicity. Yeah? Either execute all the transactions are going to be completed, executed, or it looks like it never happened or it never runs. So in this case, I need to make sure that every single transaction must either have a commit or abort in this case. So how this is, the algorithm is going to summarize how to perform the recovery. From the undo log, you start at the beginning. You need to identify all the uncommitted transactions. Then after that, you need to perform the operation for every single modification or log entry that you find in the log file. You have to, in the reverse order, you start from the latest up to the earliest. You need to do the following. Update the value of X with the before value V, because I have the value of V is here. So how can you perform this one? Write X and V. What's the write X and V? That means this transaction is going to modify the value of X, and the new value is going to be V, which is the old value that I have in the log entry. Then I need to make sure the output X, that means I need to modify this one in the disk. Make sure the change is going to be reflected to the disk. Okay? Then after you're done for every single transaction within this list, yeah, they are uncommitted. You need just to write abort. That means it's going to be abort. That means it's going to be completed transaction, of course, unsuccessfully, but it's going to satisfy the atomicity, property. When you say flash log, that means whatever you have in the log, make sure that you have the change made in the disk. If you didn't do this one and the system crashed, that means you have to repeat this operation again. So I'll give you an example. So again, in the exam, generally speaking, if you have give you a log file, and of course not small like this number, large one, and they give you for example, if you have all the database elements, I'm going to give you the initial value. For example, before I start this transaction or this log entry, we have the initial value of A equal 8 and the initial value of P equal B. Yeah? And they say, for example, the system fails, for example, at this point or at this point or at this point or at this point in different locations. So in this case, if the system is crashed here at the end, so what I'm going to do here, I'm going to tell you, for example, what kind of technique we're going to use the log entry, recovery. So here we're going to use undo. So this means I'm not interested for the committed transaction. I'm just, interested in uncommitted transaction. If you follow this algorithm, you're going to know exactly what we have to do. So I start here. I need to identify, do you have any uncommitted transactions? No. Or I have only one transaction and this is committed. Okay. So that means what kind of action I need to do? Nothing. Because remember, I don't care about the committed transaction. I'm just looking for uncommitted transaction or the reverse, any update made by this transaction in reverse order. Yeah, so in this case, we don't have problem. So what if we have this case? That what I have in the disk. This is the things or the log entry is going to be stored in the disk. Okay, and here, for example, assume the system is crashed here at this point. So at this point here. So here, this undo log, the first thing I need to look at, do you have any uncommitted transaction? Yes, we have T. Because how can I tell this one? Because I didn't find the commit here. So in this case, what action you're gonna do here? The action gonna cause by records a log, you need to reverse them. So start from the end and go backwards. Okay, so the first order you have to tell me that, for example, I need to reverse whatever, restore the value of the database element B back to the old value, V. In this case, it's going to be 8. Then I need to restore the value of 8, it's going to be 8 back. Yeah, and continue. If you have more, continue this one until you're done. Okay. So after this point, after I recover from the cache, what I'm going to do here, what the result, what the value of A and B, the value of A, we start the value of A, in this case, for example, equals 16, and the value of B equal, let's say, in this case, maybe is, I'm not sure, it's going to be 8, 8, and I restore them into 8, 8. So what if we have something like this? You have nothing in the log file, in the disk. Don't look at the main memory, because if the system crash, whatever you have in the main memory, whatever you have here is done, whatever you have here is gone. Okay? So the only thing I need to do, every time the system crash, the database management system or the recovery manager is going to try to do what? Try to fetch the block that contains information about the log entry from the disk to the buffer in order to start processing, try to recover from the system. So here, what do you have here? I have nothing. Because the log entry is empty, nothing, there's no log records. That means there's no transaction, there's no, uncommitted transaction. So what kind of action I need to perform? Nothing. Okay? Okay. So what happens if, for example, you try to recover from this, recover from the crash, and the system crash again and again and again? It doesn't hurt. Remember, we can say this one is idempotent. That means what I'm trying to do here, if I did this one 1,000 times, was this going to affect me? No, because I always restore the value of B back to the previous value and restore the value of A back to the previous value. If I do this one 1,000 times, 1,000,000 times, it's not going to hurt me. In other words, if you, during the crash recover, the system is going to be crash again, it's going to... we being able to restore to this one to the previous state. Because we keeping restoring the old value back into the database element, with this operation idempotent. Okay? So in other words, we can simply reapply the log to the database again and again and again, and it's going to have the same effect. Okay. The problem here, I give you just example, a simple log file, and this log file has only few elements or few entries here. What we have here, million of records here. For example, you have to scan from the end up to the beginning, yeah? So the size is going to be larger and the larger. Remember, we are not going to delete anything here. We just append. In other words, whatever any change or modifications, the system must be have a log entry is going to tell me what happened at the time. What we did, every single transaction, what we modify, or it modifies, or what we change in the database element, in order to allow me to recover from the system. So the problem, if you take a look, we need to every time to when we try to recover from the errors or the crash, I need to try to scan the entire log entry. This is going to be tedious because it's going to be long entries here. So can we make this one shorter? Reduce the size somehow? Yes. We can do using what we call, the log checking here, which, this will allow me in order to reduce or truncate, the log from time to time. For example, you can say, right now, whatever you have up this point, you didn't need to go, for example, beyond this point. I give you like special entry here. And if you put this one in the log entry, it's to tell you that you didn't need to waste your time to go beyond this point, because whatever you have before this one, we magically, yeah, we recover from this one. So you don't need to find this entry. We're gonna see how can we build this, or to reduce or truncate the size of the log file or log entry. So we call this one the log, checkpoint, okay, or checkpointing, which allow us in order to short the size of the log file, okay. And when you say by removing, I'm not gonna delete them. I'm just like, it's not physically. It's like, it looks like, logically, okay. It looks like you have like a special marker, this log entry in specific place, and allow you to decide whether you're gonna go beyond this point or stop at this point. Okay, so we are going to do what is called log checkpoint log record with a special log entry or log record into the log file. Okay, and it depends what kind of log checkpoint we're gonna log entry we're gonna store or we're gonna put here. Some of them is gonna allow me tell me that all the log records before this special or the log record is not required. That's means in order to allow to help you to recover from the errors. In other words, will not be examined in the recovery procedure. Okay. And again, it's worth mentioning here why we need to keep all the, let's say, the log record into the log file, because sometimes we use this one in the auditing or maybe in the accounting, in the banking transactions, in the banking, for example, system, try to have like all the log entry, all the modification, all the transformation or transaction that made in the bank in order to make sure that no one is gonna try to cheat or try to play around. Anyway, so its special checkpoint or the log entry, it's going to be stored in the log file, and it's going to help us during the recovery operation. It looks like we try to save our time. Instead to scan the entire log file, we're gonna let's say scan maybe portion of the log file. Okay, so let's show you how can you do that. So I'm gonna show you how to do the checkpointing in the algorithms for the undo right now. So if this is the log entry, okay, of the log files. If you find, say, commit for transaction, what does that mean here? That means the undo, these records get stored here. We call this one undo records, which allow me in order to recover from the crash and do whatever this transaction, any transaction, update or modify the database elements. So in this case, if this transaction is commit, I found commit with this specific transactions, that means all the log undo log records that are written in this log file is not important for me. Yeah, I don't need it. It's unnecessary. Okay, because remember we said the commit, if I commit T entry, that means it's evidence proof that the transaction is done. It's completely successful. Okay, and I'm trying to undo whatever the uncompleted transaction, not completed transaction. So how can you truncate this one? The simple thing, I need to find, let's say this one way, I need to find this is the first uncommitted transaction in the undo file. We start from the beginning here. This is the undo log file. You start from the beginning. Local for example, I have a TM, and this is a committed TM. Then after that, I found TK, for example. I have another transaction. Did I find any uncommitted? Commit for this transaction? No. So I will find the first uncommitted transaction from the undo log from the beginning. Then what I'm gonna do here, if you find this one, what does that mean? Whatever log entry is going to be stored before this one, do I need it in order to recover from any errors or the crash, the system crash? No, because all the log entries or undo log entries before this point, this belongs to committed transaction. Okay? We do have, so how can you perform, or how can we truncate, this portion, or say this, whether I need it or I don't need it? I'm going to show you two different techniques. The first one, quiescent checkpoints, and the second one, non-quiescent, checkpoints. Okay, the quiescent, checkpoint is a simple way. That means here is inactive. That means I need to make sure that no transactions are running here in this case. How can we do that? So this is the algorithm. Make the database management system stop accepting any new transaction. That means it looks like now I decide, for example, at this point, I need to write, let's say, checkpoints here. When you decide at this point, that means as a database management system, stop accepting any new transaction. So that means I'm waiting all the active transactions that's still uncommitted, and completed until they are committed or aborted. In other words, must be completed first. And remember, I'm not going to accept any new transaction in this case. Sorry. Then wait all the, as I mentioned, all the currently active transactions, they're still running at that time, still running until they commit or abort. Then after that, flush the log to the desk. This means whatever you have entry in the main memory must be flushed to the desk. Then after that, I'm going to write special checkpoint here as a log entry. What does that mean if we have a checkpoint here? That means before this point, or the portion of the data that before this point, do you need it in order to the recovery? For the cache? No, I don't need them. Okay. Then after that, now we can start accepting a new transaction. Again, for the quiescent here, assume that we have this log and log here. At this point, we decide to add this checkpoint. So first, mark what this list all the active transactions. Active transaction, that means any transaction they didn't find to commit or abort at this point. So with the active transaction, we have T1 and T2. Stop accepting any new transactions. Wait until T1 and T2, done from the execution, either completed or let's say successfully, unsuccessfully, abort or commit. Then after that, I'm gonna write the checkpoint. Then I flush this one to the log. When I flush, that means make sure this entry is gonna be stored in the desk. So this is an example. Assume that you decide, for example, at this point you need to say insert the checkpoint. So this is quiescent. That means wait until all the transaction T1, T2 done. When they are commit, that means I need to write the checkpoint. Then now starting accepting new transaction. That's it. Okay. So what's the benefit to using this one? When you try to recover of something you cache in the system, this is gonna be available to you, yeah, because you're gonna retrieve this information from the desk. Okay, so if there's a crash happen in the system, what we're gonna do here, you start from the bottom, from the end of the whatever the log entry, and you try to scan up to the beginning. Just you need to identify all the uncommitted transactions. When I start scan in the reverse order from here, I reach this point. I found the checkpoint. What does the checkpoint means here? This means here you didn't need to go back beyond this point. All the portion or the log entry, undo log entry that's written before this point is useless in your case, because all of them belongs to let's say either it's going to be committed or abort transaction. In other words, belongs to completed transaction. So this means you don't need to touch them. Okay, so it looks like you find a way in order to truncate or reduce the size of log file. So in this case, I need just to undo this part of the operation. Okay. There is another way, because the problem with the quiescent, the checking point or technique, this is going to make the system ideal for a period of time. That means I'm not going to accept a new transaction. I will stop processing or accept a new transaction and the previous one or the current one done. What I'm going to do here right now, we have a different way. We call this one non-quiescent, checkpoints. So this one is going to perform the checkpoint without stopping the database management system from accepting a new transaction. So in this case, I don't care. I'm keeping accepting new transaction, but I have a smart way in order to, reduce or truncate the size of the database. Say the log entry here. So here, this is the algorithm. For example, if you decide from time to time, okay, you decide you are going to add or start a checkpoint log record. So you have at the beginning, you say that specific part, moment of time, you say, now I need to start a checkpoint, a log record. So what you have to do first, you need to list all the active transactions right now. What the current active transaction are at the moment that I decided also to start the checkpoint. For example, T1, T2 up to TK. Okay, list them, and we have the log entry. It's not checkpoint, it's going to be start a checkpoint. So it looks like we have two entries, one of them is start and the other one we call is going to be end. Okay, so for the start checkpoint, again, I need to list all the active transactions at this moment. Then after that, flash log optional, we're going to see I don't mainly care about the start checkpoint in the same degree that I care about the end checkpoint. This one must be reflected at disk. Okay, so this one is flash log is going to be optional. Whether it's going to be stored this one in the disk or not, you need to make sure that, as I mentioned, we're interested more in this part, in the end checkpoint. Anyway, so I list, for example, at the start checkpoint, we have, for example, let's say T1, T2, and TK, for example, okay? They are active. So I'm going to wait until all of them are going to be completed. Either it's going to be successfully or unsuccessfully, okay? Either going to be commit or abort. Then after that, I'm going to write, the end checkpoint. So I'm not going to write the end checkpoint log enter until make sure that all the transactions at the moment that I decide to start that start checkpoint are done, are completed, or let's say either successfully or unsuccessfully, I don't care. Then after that, now you have to flush the log. That means I need to make sure. Why I need to this one essential? Because I need to make sure the end checkpoint is going to be written to the disk. Okay? So let me show you how to do that. So for example, you decide, for example, in this moment that here I decide to add a start checkpoint. And you talk using the non-quiescent here. So you have to do what? You have to write a start checkpoint here. And what the list, you need to list all the uncommitted transactions, uncompleted, which in this case the current or active, which T1 and T2, because I didn't find any commit or abort here, write them here. Then after that, wait until these transactions gonna be commit or abort. That means you have to find between the start, the checkpoint, we have to have two commands. One of them is gonna be commit T1 or T2, or we have abort T1 and T2. Must be something related to the T1. Then after that, write the end checkpoint. Then after that, flush the log. So this is an example. And try T1 and T2. I will wait until the T1 and T2 either going to be commit or abort. Then here I'm going to say end the checkpoint. It's worth mentioning here that during this process, I can, or the database management system can accept a new transaction. So we can have a T3, T4, whatever. It's fine. We accept. Yeah? So how can you use this one in order to recover? And remember, you can use the old one, but this one is going to be more efficient because it's going to allow me to, I don't need to read the entire, the log entry in order to, or log file, sorry, in order to undo the, or recover, let's say from the cache here. So I'm going to show you, it depends on you. Yeah, for the T3, it depends on you. We just started for the checkpoint 2 here. For the start T3, after you end the first one, so any moment or any place after the end checkpoint, you can, if you want to decide to add another start checkpoint belongs to another transaction. So for the T3 or whatever, you can start after the end checkpoint if you want. But we don't do this one next to each other. It's like, let's say you can wait until the log file that has reached specific size, or the number of entries from the last end checkpoint is going to reach specific size, or number of log entries. So in this case, you need to do this one. Yeah. So we do have two cases here in order to use this one in order to recover. The first case, you start from the bottom, reverse order. First entry you're going to find here from the bottom, reverse backwards, you're going to find the end checkpoint. Or you go back, you didn't find the end checkpoint, you're going to find the start checkpoint. Because sometimes when you start this process, the system is going to be crashed. So there's a chance that you're going to find a start checkpoint, but you are not going to find the, corresponding end checkpoint. So we have two scenarios. You're going to look at them, and you're going to see how can we recover or use them in order to recover from the crash. So the first one here, you start, scanning from the end, okay, or the backwards, then you find the start checkpoint, the end checkpoint. What does that mean here? This means that the last checkpoint operation that you started has completed successfully. Because you start checkpoint, wait until all the transaction completed, then after that, you end the checkpoint. What if there are second scenarios here? You scan from the end or backwards, and you didn't find the end checkpoint, you find the start checkpoint. So that means in this case, the system has been crashed during the process or during the operation of the last checkpoint. How can you use this? Or what does that mean in this case? And what does that mean in this case? I will show you here. If you found, the end checkpoint entry in the log file, what does that mean here? As you mentioned, the last, the checkpoint that you started is gonna has been successfully. What does that mean here? That means all the transaction here. That means whatever the portion of the data that belongs before the start checkpoint, I don't need it. Do you need it? No. Because remember, when you start this operation, that means we record all the transactions were active at that time, and I wait them until all of them are going to be completed. Then after that, I write the end checkpoint. and I'm interested only to redo and let's say uncompleted transactions. So I'm gonna start scan from the end up to reach this point. I'm not gonna go beyond this point here, because again, any transaction start before the start checkpoint here is gonna be listed here as an active transaction, and it's gonna be completed or aborted. I mean, successfully or unsuccessfully. Yeah. So again, the portion of the data that for the undo log that before the start checkpoint here in this case is not going to be necessary. You can do it, I mean, but it's not necessary, because I mean all the transactions are committed, yeah, or let's say aborted. So in other words, are completed. That means you are not going to redo undo whatever they done. In other words, you never find an let's say incompleted transaction before the start checkpoint, if we found that in the checkpoint. Yeah, so that means in this case, in order to recover here, I will start from the end up to this start checkpoint. Yeah, clear, guys? Okay, so the second one here, you found only, I mean, the start checkpoint here. There is no end. What does that mean? If you found this one, I know at the time I start this process, I list all the active transaction, but can I guarantee that all of them is going to be committed and finished? No, I cannot do that. So in this case here, there is a missing endpoint, so I cannot make sure that all the change made by this transactions is going to be reflected to the disk. That means in order to recover this one, in order to make sure that I'm talking about, incomplete transactions. Okay, so in this case, you need to do what here? You have a list T1, T2, a list of all the active transactions. So you need to go back. So the portion of the data or the log entry that before the start checkpoint must be visited, must be checked, in order to make sure that I need to recover or undo all the transactions made by uncompleted transactions. Okay? Okay? So again, if, for example, let's say you have T1 and T2 here, and here somewhere when you start here, you found T1, for example, is complete, is let's say committed. Do you need to undo this one? No, I don't care about this one. Now for the T2, all the list of the transactions are listed here at the start checkpoint. They are not the ones that are not completed here. I need to undo them. So how what does that mean if these transactions are listed here? This means they start somewhere before the start checkpoint. So I need to go back until to find the first start for the transaction that listed in the checkpoint. Then this is going to be the portion of the data I need to use in order to recover from the uncommitted transaction. So again, we have T1 and T2 here. I need to find the start checkpoint first. Then after that, what I'm going to do here, find the earliest starting transaction among this set here. For example, you have T1 and T2. All of them there, for example, they didn't complete it here. So I need to go back. I need to find when the T1 start, when the T2 start, and make sure that go from the end up to the earliest starting transaction among the set of T1 and T2. Which one start first? That means this is the portion of the data I need to scan in order to recover from there. What about the portion of the data here? I don't need it. So in other words, we're still being able to reduce a portion of the data that of the log entry that we need to visit in order to recover from the errors. Okay? And this is again the portion of the data you need to log into. So how far, for example, back you need to scan to find all the start checkpoints record? For example, you have a list of, list of transactions here was active at the time. I need to find the way how far back I need to scan to find all of them. In the worst case scenario, you have to go back until to the previous start checkpoint, because these transactions, how early they can start, before, after, the previous start checkpoint. Okay? Because if there is previous start checkpoint, you cannot start one until you make sure the previous one is done. So the previous one definitely gonna have like the end checkpoint. So all the transactions listed in the previous start checkpoint definitely gonna have, let's say, gonna be committed or aborted before this operation. Okay. As I mentioned, next section I'm gonna give you example. The example is gonna give you more details. We have some checkpoints here, and you're gonna see how we use this one in order to recover from the errors and etc. So there is an issue using an undo logging. It's going to only to undo the, let's say, the committed transaction. We don't have a problem here, but the problem here for every single, let's see, show you an example here. Here, for every single log entry you get found here, undo log entry, or undo log, let's say, record or entry, we have to do what? I need to store the value of the database element B back to 8. And I need to do that, the same one for the A. When you store this one, that means I need to write, perform output. I mean, write B and 8, then after that you have to say output B. What does it mean output B? That means take the block that store the database element B and store this one to the disk. For example, if we perform this 1,000 operation, or we have 1,000 database elements, all of them reflect or are modified by specific transaction. I need to undo all of them. That means I need to perform 1,000 disk commit out operation, which is costly. Yeah, that's a part of the undo here operation. I mean, log file. So an undo logging, again, requires that the database or the data or the elements must be written to the disk immediately after the transaction finished. Perhaps increase the number of disk out operations that need to be performed. When you perform the undo, that means you have to reflect the change. And also the same thing here. Every time you modify the database element, if you have one output, you need to write this one to the disk, you have to do it right now. You cannot wait. Yeah. So how can we solve this problem? We can use what is called, I mean, the redo logging method. So just I need to compare between of them to see what's the difference. For the undo logging, it's only designed or only to undo or cancel or roll back, I mean, the effect or change or the update of incomplete transactions. Yeah. Here, for the redo logging, it's different. It's designed only to redo, to repeat, to do it again. Okay. Whatever the effect or the update made by the completed transactions. Okay, so in this case for the undo, recovery procedure just ignore all the log entry that belongs to the committed transactions. Here in this case, the recovery procedure will ignore the uncommitted transaction or the log entries. So if we have redo logging, if we found, for example, you're gonna find in the log entry there, the log file that mixed information that belongs to the committed or uncommitted transactions. So in this case, if it's redo, I need to just redo the committed transaction. So what about the incomplete transaction or uncommitted transaction? Just ignore them. Okay. So again, how can we write this one? I'm gonna show you, the operation, what kind of operation or the record types you need to be stored in the redo logging. Then show you, for example, whether we do have a writing rules that's gonna specify the order when we need to reflect the change to the disk, when you need to, the store, reflect the store, whatever we have the log entry in the main memory must be stored on the disk first before modify make the change. Okay, we have start, commit, and abort the same record type entries that we did before with the undo. Start transaction T, commit transaction T, and abort transaction T. The main difference here, we have this the log record T, X, and V. What do you need here? I need to redo the action, modification, or the change made by this transaction. So in this case, I'm gonna keep tracking for the new value for the database element. For the undo logging, we are going to keep tracking, or we need to store, the log entry or log record that store the previous value of database element. Here, I need to have piece of information, extra piece of information allow me to redo the action. That means, makes sense, we are going to store the new value of X. So here, transaction X, modify the database X, and the new value of X is gonna be V. Okay? So, let's take a look to the rules that we have here. We do have one rule here. We call this one the log update rule. The transaction manager, okay, can only perform the output operation for the committed transaction. In other words, you have to wait until the transaction is completed in order to reflect the change made by this transaction to the disk. This is the meaning here. So if the transaction manager performs the output X, that means I need to change, modify, reflect, change of database element from the main memory to the disk here. So the transaction manager must first write all the log records of the transaction T to the disk. That means all the log entry that belongs to the database. This transaction must be written to the disk here. before I'm going to write the output here. So in other words, before do the output X, whatever database elements that modified by this transaction, we must flush out the log record of the transaction T. In other words here, I need to keep tracking for the log entry there. In other words, I need to make sure that I need to store the piece of information that allow me in order to do that action made by this transaction. Okay, so the simple thing, we start at the beginning here. I have the operation output X, for example. The transaction tried to modify the database element X here. I need to make sure that first, whether the transaction, I'm not going to reflect, it looks like you are going to delay, the output or modify the database element in the disk until you make sure that transaction is completed, is committed, is done. Yeah, so I check, the database, the state of the transaction, whether the state of the transaction is committed or not. If it's not committed, that means delay the output. You are not modify the database element because we need to wait this one, make sure that it's going to be committed. So if the database element or the state of the transaction is committed, then in this case, what I need to do here, I need to write all the log records. You remember, we need to make sure this load is going to decide when you need to, write the log record from the main memory to the disk. And they need to have something in the disk in the log file in order to allow me in order to recover from the cache. Yeah. So here is going to write all the log record to the disk. Yeah. How can you enforce this one? Flush log. Then now, if you flush log, that means you're gonna write start X, T, X, and V, whatever value they change. Then after that, you have a commit T must be stored in the disk. Then after that, now you can change the database element X. So here, why you delay this one until we make sure that all the log records is going to be written in the disk? Because this one, if any system failure happen or crash happen in the system, so we can go to the log records that file that's stored in the disk, fetch to the main memory, and you find that all the committed transaction we have all the piece or all the information required in order to to redo the update or modification made by this transaction. If the state of the transaction not committed, that means don't write right now, delay this one and to make sure the transaction is committed. Else you continue perform the rest of the operation that we have. So take a look at the example here. So here, for example, assume that we have a start, we have this transaction start and modify the database element A and B, and notes here, this is redo log that I'm keeping, the new value of A and the new value of B. Okay. Did I change anything in the disk? No. Everything is changed in the main memory and the transaction buffer. This memory space. If the transaction, for example, say, now I need to output A. Before you do this one, what you have to do here, you need to make sure that the log entry, before you modify the database element in the disk, you need to make sure the log entry must be stored in the disk first. You need to have a guarantee, I need to make sure that insurance that store this piece of information in the disk. So if anything bad happened, I'm still being able to redo the action made by this transaction. Okay, so in this case, I'm gonna flush. The log. This means whatever you have in the main memory, you now enforce the buffer manager in order to store this one in the disk. So store the disk right now. Okay, everything, and it's a commit. Then now you can do output A, output B, modify the data in the disk. Okay, so if something bad happened after this point here, we're still being able to do, whatever change made by this transaction because I have all the piece of information here. Okay. So question here, if you found to see the commit T here, maybe someone wondering, they say, why you need to redo this one since this committed here? If you found a commit entry in the log file in the disk, doesn't guarantee that the date we change, the change made by this transaction is going to be reflected in the disk. Because what if after you perform the flush log here, we have a commit T, the system crash here after the line 9, between 9 and 10. So in this case, did we change any database element here? No, we don't. So that means in this case, doesn't mean that you have a commit T in the log entry in the disk, means that we'll guarantee that the data or modification made by this transaction definitely reflect to the disk. That's why you need to redo it. Okay, so how can we recover this one here? So again, you need, in this case, in the undo, you need to do what? You need to, I need just to remove the N. Okay, anyway. So I think you need to fix this one. In your case, maybe is undo, I guess. You just make sure this one redo. I will update the slides after the class. So here the first one is to what? I'm interested only in the completed transaction. You need to identify them. How many committed transaction you have, committed, yeah. Then after that, you are going to do this transaction. So you have to beat the change or effect of this transaction. I start from the beginning to the end. This case is not in the reverse order. I start in the forward order, in redo. And for every single transaction, committed transaction, you need to update the value of X with the after value of E. Can I do this one? Yes, because here, for example, start at the beginning. In this case, I have only transaction T is the commit. I need to redo this one. So I start from the beginning. I need to do what? Write A and 16 and output A. And write B and 16 and output B. Yeah, that's what we're going to perform here. Then after that, for all the transaction that is uncommitted, that you found it, you need to do what? You need to abort them. And again, I mentioned this one before for the undo technique, and you're gonna repeat it in the redo. The reason behind this one, you need to make sure that atomicity is, guaranteed for all the transactions. Either it's gonna be completed or it's gonna be incomplete. Either it's gonna be committed, or aborted. We don't have a transaction. We are not gonna leave a transaction like it's not incomplete, it's not aborted after I recover. Make sure all of them gonna be finished or never exist. Okay, so assume that we have a D-log here, this information given to you, the log entry here. Then assume the system crash here, fails here, after this point here. So what I'm gonna do here, first I need to identify all the, committed transaction. In this case, you have only T. Then after that, the order is very important. You have to start from the forward, from the beginning here. So first you need to update the database element A to the new value 16. Then you have to say update the value database element B to the new value 16. For me, if you have a question like this, you have just to specify, for example, I'm going to perform this operation. So A equals 16 and B is going to be equal 16. Something like this. Show me what the action and show me the order of this one. Okay. So now, again, this size might be too large, too huge. Can I reduce the size? Yes, using the checkpoint. And we are going to interest in only the non-quiescent checkpoints, okay, technique. So how can you do that? Remember, in the checkpoint log, what you need to do here, you need just to reduce or need to shorten the log file or the log file using what? By logically, removing the log records of the completed transaction. So I need to find a way in order to removing the log records for all the completed transactions, even here. Because I need to find a way that, for example, instead to waste my time, and instead in order to redo all the committed transactions, maybe you have magically, you can find a way in order to say, up to this point, for all the committed transaction, we found a way to guarantee that the change made or reflect to the disk. That means there is no need to waste your time in order to redo it again. Okay? So how can you do that? So just to remind you, for the abort, this means the transaction is completed, unsuccessful. Okay? And if the transaction is completed unsuccessfully, that means this transaction never performed any output operation in the redo logging. Yeah? Because remember, in the redo logging, when you try to build your entry here, when your transaction tries to perform output, I'm not going to execute the output until make sure the transaction is committed. Since the transaction is abort, that means I don't have this output entry here. Yeah? And again, the output operation committed transaction in redo logging can be delayed. That's what we did here. So let's see how can we do it right now here. We can delete, when you say delete, this means to say logically, okay? The record belongs to uncommitted transactions. Okay? In order to remove, the redo records belongs to the committed transaction, we need to do the following. Okay? The first one, we need or must first find all the update, make sure that all the change made by this transaction, we need to make sure that to find a way, and the change must be reflected to the disk. Okay? So how can you do that? So again, the same structure or the procedure at the beginning. It looks like you have two new entries. The first one, we call this one the start checkpoint, and the other one we have as end checkpoint. For the start checkpoint, you need to list all the active transactions. That means uncommitted transactions still running at that time. Then I need to flush the log. This optional. Then make sure that you need to make sure all the, let's say, all these transactions, okay? I need to make, let me give you an example here. So at the beginning of this point, I say, let me start here. Let's say checkpoint. I have T1, for example, T2. Okay? Then after that, in this point, what I need to do here, I'm not going to say the end until make sure. At this point here, do you have any committed transaction? I'm not talking about the T1 and T2. I'm talking about any committed transaction before this point. If there's any committed transaction before this point, I need to make sure that the output of all the database elements that were updated by the committed transaction must be reflected at disk in this point, this area. Once this operation is done, I can write in the checkpoints. Yeah. So again, when I try to use, add the check non-quiescent checkpoint for the redo lock, I need first to start the checkpoint and list all the, let's say, the active transactions right now. Then after that, I'm not gonna write the end checkpoint until make sure that all the committed transaction before the start checkpoint must be reflected at disk. That means somehow I can enforce what's called the output operation for all of them. For whatever database elements x1, x2, xt, whatever these database elements that were modified by the committed transaction that before the start checkpoint. Okay, so let's see example here. Then after that, flush the log. So this is an example here. Assume that to start T1, you have to start T2 and commit. We decide, for example, the size is too large. That means we decide to add this checkpoint here for the redo log. So I'm gonna start checkpoint. How many active transaction here? We have only T2 because the one is uncommitted yet. Then I will add this one here as entry. Then wait until all the change that modified by committed transaction. First, how many committed transactions do we have? We have only T1. What the T1 did, modify how many database elements. And before this commit, before the start checkpoint. For example, modify A, B, C, D, whatever. Then I'm gonna make sure that write A and write to the disk. Make sure the system, I'm not gonna add that in the checkpoint until the system is gonna issue the output to say A. And the output B, output C, whatever database element modified by this transaction. Then after that, I put the end checkpoint, and then I flush the log. So in this case, if you found any end checkpoint, that means go back to the start checkpoint, that the previous one, and this guarantee that all the transactions committed before this point, definitely their change has been made to the disk or reflected the disk. In other words, there is no need to redo them. Okay, so assume that some transaction going to be, for example, start after that start checkpoint is okay, because remember, non-quiescent here we allow that the database management system is going to allow to receive or new transaction going to be start. It's okay. And later for the commit T2 and T3, maybe later if you prefer the output operation for them, maybe it's going to be happen later. So let's take a look. How can we recover using these? Non-quiescent checkpoint for the redo here. So again, we do have the same. Two cases. Okay. The first one, you start scanning scanning backwards from the end of the log file until the beginning. This is the usual case that we have. But now using checkpoint, hopefully this one is gonna reduce a portion of the data that we are not gonna use in order to perform the recovery. So reduce the size of the log entry or the log file. So we start in the end backwards. I found either we're gonna find, I have two scenarios. Either we're gonna find came across the end checkpoint or the start checkpoint. If you came across the end checkpoint, this means the last checkpoint operation has been completed successfully. If not, this means the last one hasn't been completed successfully during the process of starting the start checkpoint. Something happened or the system is crashed. Okay, let's see. We call this one case 1 and this is case 2. How can we deal with both of them? For the case 1 here, when you start this operation here, what does that mean here? If we found it in the checkpoint, means that all the transaction that has been, let's say, committed before the start checkpoint, we guarantee that their effect has been written to the disk. That means there is no need in order to redo them. Okay? For example, we have an example here, the transaction T, and this committed before the start checkpoint. That means within the start checkpoint and end checkpoint, remember that we have to write all the change, or update all the database element that modified or touched by this transaction or committed transaction. In other words, we are going to perform output. So that's like a guarantee because we have end checkpoint here. Then that means this part of this portion of the data that's before the start checkpoint that belongs to the activity has been done by committed transaction. We didn't need this log entry. Okay, so but we need. Does that mean that we don't need the whole portion of the data that here? We don't need only the portion of the data that related or that record. The activity has been done by the committed transaction, but we still, since we have some active transaction at that time was there, for example, T1 and T2, we need a portion of the data in order to try to redo the T1 and T2 if they, committed after the start checkpoint. Again, for the redo, log file, we need to do what? We need to redo the committed transaction. So again, we still have to redo, all the updates made by the transactions that are committed after the start checkpoint. For example, we have T1 and T2 was active at the time, then after that they're going to commit after the start checkpoint, and either before or after, we don't care. Since we are going to start with the end and backwards until the start checkpoint, I need just to find out or list out all the committed transactions and see which one is committed, which one is not. If I found one of them committed, I make sure that I need to find the earliest start transaction in order to make sure that I need to redo all the transactions made by this. The transaction was active at the start checkpoint. So again, find the earliest start TI log entry or log record, where TI is the one of the entry of the the transaction that was active at the moment when you start to do the checkpoint. You do all the updates made by these transactions that has been committed after the start checkpoint. So back here, if we have, for example, T2 here and T1, both of them are committed because they started the end. So when you need to perform that, I need to find out which the earliest start checkpoint from the T1 and T2. So that means you have to go back here before the start checkpoint in order to identify the earliest start point. Then after that, you have to redo from this point up to the end. For the case 2, if you start scanning backwards and you came across the start checkpoint, and again this means you try to during the process of the operation to start the last checkpoint, something happened, the system crashed. That means in this case there is no end checkpoint. So it looks like here we don't have start checkpoint at all, because any committed transaction before this start checkpoint, we cannot guarantee that their change has been modified or reflected to the disk. We cannot, yeah. So in this case, without, again, in the checkpoint, we cannot tell. So the worst case scenario that there's no updates at all has been done or reflected the disk by, for all the database element that has been modified by any committed transaction. That means it looks like we have to go further back into the redo log and the recovery procedure from the case 1. So it looks like we have to do the same thing as the case 1. So we continue searching. If you find, for example, let's say the last end checkpoint for the previous step of the one that before this operation, maybe we have before this, for example, start checkpoint multiple times or many times to go to the previous one. They have to do. It looks like we have to do the scenario 1 again or case 1. So again, we start to have two different logging mechanisms. The first one, the undo logging, and the second one, the redo logging. Okay, the undo logging is going to do what? It's going to undo. The transaction has been made by the effector has been made by the uncommitted transaction, and the redo is going to for the committed transaction. So redo all the action or activity. Undo logging, that looks like you have a drawback here. That means cannot bring back up, database copies up to date, because remember, I need to roll back whatever to all the previous, consistent state for the database. For the redo logging, it looks like we need to keep all the modified blocks in the memory until commit. Remember, you cannot write or modify the database element until you make sure that we have the database, the transaction is commit, yeah? Once the transaction commit, you can perform the output. Remember the right rule that we came up in order to create or came up in order to generate or create a redo logging file. Can we do better? Yes, we can combine both of them. We can come up with a technique that's going to do undo and redo at the same time, which is the one that we need to cover more details, and they do have maybe 2 examples to cover this one. So the format of undo and redo log record looks like we need just to modify the log record. For the undo, we used to have the previous value. For the redo log, we need to have the log entry that has the old value, the new value. For the undo redo, I need to have enough information that allow me in order to perform the both of operation at the same time. So in this case, I need to what? I need the old value and the previous the new value for the database element that has been modified by the transaction team. So it's going to be listed in one log record. So here looks like this undo redo log is like a combination of 2 logging approach or techniques. Yeah. So we do have only one write rule, which looks like similar to the writing rule that we have for the redo, but we have one exception. So the undo, redo log record, that's write the log record. Remember, before you modify any database element, you need to make sure that we have enough information stored in the log entry. That's what we try to do here. That means write this log record that allows me to recover from the crash to the disk before you modify or writing, or updating the database element to the disk. In other words, before you're writing the output X, you have to make sure that we have this log entry written to the disk first. And again, it's just to remind you, the log, the log writing rules that we came up with, was the rules that allow us in order to control when we need to flush, the content of the log file that's stored in the main memory into the disk. So this, just the algorithms to cover, these, the old single rule or writing rule. So here you start if the operation is output X, where the transaction try to modify the database elements. We need to make sure that we said, wait, write all the log entry to the disk, including, T, X, and V, and W, the new and the old value. In other words, whatever you have in the log entry that's stored in the main memory, you have to store this one to the disk before to make sure modify any database element, which makes sense. Because I need to have some piece of information or something or useful information to help me to recover with the crash. Before I modify anything, tell me that I want to modify the database element and this is the old value, this is the new value. Write this one somewhere, then start modifying this one. If you didn't manage to do this one, so I can't go back to the log entry or log file and use this information in order to recover from the error. Okay? Then after that, you can output to modify the database elements. Otherwise, you can perform the operation. So here we have only one rule, okay? So I give you an example, quick example here. For example, this is the actions, the same thing that we work with, and this is, the main memory log entry that's going to be in the main memory. So what we try to do here, we have 2 database elements A and B. We need to deduct or take $100 from, let's say, account B or database element B and store this one or deposit this one in the database A or database element A or the account A. Okay. So here we start the transaction. At the beginning, it's the log entries, read the database. There is nothing here. Remember, we just need to store start, commit, report, and we have like just the write operation. So you take the database element A was 1000. Now fetch this one to the main memory. Then from the main memory to the local space or memory space for the transaction. Perform the operation locally. Then here, when you say write A and T, update the database elements in the main memory. Just we have 1100. Then after that, we have to take the base element 2, then deduct $100 or whatever. Then you need to update the data. So we modify all the database elements at the main memory. Now, if we try or transaction try to output A, that means you want to reflect the change that we have in the memory into the disk. That means you need to update the database element. And here, remember, for every single writing operation, we need to keep tracking, or store the log entry as following. So you have transaction A, T modify the database element A. This was the old value, and this is the new value. And the same for the database element B. This is the old value, and this is the new value. Okay, when you try to perform output A, you cannot do this one until make sure that all the entry must be changed to the, reflected to the disk or stored to the disk here. So that's what we did here. We make sure that when you try to perform the output A, you have to flush whatever you have in the main memory log entry into the disk. How to perform this one? You have to do this one using the flush log. Okay, then after that, now it's fine. Maybe you notice that here we don't need to have whether the transaction is commit or not. What do you mean the transaction is commit? That means the transaction is done. There is no more operation to perform. That means I don't have any. I'm done here. But in the writing or redo log, we have to make sure we are not going to reflect the change only to make the database elements. The transaction must be committed. But here we have a flexibility. We have, before you modify or update the database element in the disk, you have to make sure that to flush whatever you have in the log entry that store the main memory into the disk. So there is no need to wait until it's going to be commit or not. Okay, so the output A, that means now we managed to can modify the database, reflect the change to the disk for the database element A. You can commit here, maybe the entry is going to be here, that's fine. Then after that, you try to modify the database element B to reflect the change to the disk. Before you do this one, basically the writing goal, you have to flush the log. You have to make sure whatever you have in the log must be stored in the disk. And remember, at this moment here, we have only one entry in the log file that's stored in the main memory. That means you are going to just write the commit here. And here we have continue output modify the database element B. Okay. So how can you recover? Which is very important here. The recovery here, that algorithm for the undo redo log, that means we need to find all the uncommitted transaction and find all the committed transaction. Remember, this one is going to be, it looks like we have 2 and 1. You are going to undo and redo at the same time. Make it easier for you, just try to split this one into 2 parts. You have, for example, you need to take care of the uncommitted transaction, and they need to take care of the committed transaction. Each of them, they have different procedure to work with, okay? Remember, the committed transaction, you have to do this one in forward. And the uncommitted transaction, you have to undo this one in reverse order. And for the committed transaction, you need to do what? You need to redo the action. That means you have to update the database element with the new data, with the value. For the uncommitted transaction, we need to do the opposite. We need to just to store the previous value that known for the every single database database element. Okay, so find all uncommitted and committed transaction, then update or undo, you say the uncommitted transaction, and you need to redo the committed transaction. How can you do that? I will make it easier for you. So if we don't have any, let's say checkpoints, if we give you something like this, then you need to make sure what do you have in the database, log entry that's stored or log file that's stored in the disk. And basically the information that we have, for example, if the system crashed here, for example, after this point, yeah. So what I need to do here, I need to do what? 2 things. I need to scan for the backwards and identify what do we have. We have a committed transaction and uncommitted transaction. So we have, for example, both of them. It's got maybe transaction T, for example. Then you need to, in this case, actually we have only one committed transaction, yeah, because we have only transaction T because we have this commit here. So what I have to do in this case, I need to redo this one from the beginning. So keep doing this one again. So it looks like you have to say the database element A equal 1100, and then after that you have to say the database element B equal 1900. Assume that the system crashed here at this point here. So this is the only have from the start up to this point. We don't have the commit. So in this case we have, do we have a committed transaction? None. Do you have uncommitted transaction? Yes, we have, which T in this case we do, so assume that the commit is not here. So you need to redo this one. So how can we do this one? The operation, all the modification has been done by this transaction. I will start from the reverse order. So I have say B equal 2000 because they have the old value. Then after that I'm going to say the database element A equal 1000. Okay? I didn't give you example because we're going to take a look to the more complicated one using the checkpoint. Then after that, we're going to come up with 2 different examples. Okay, so how can you do this one? Reduce the size of the log file that I have. Non-coercent, checkpointing here for undo and redo log. Okay, so here the same thing. When you try to perform this operation, you have to, when you decide this at this moment, this is the best moment in order to add, when you say right, a start checkpoint. So you have just a start checkpoint. Then after that, list all the active transactions. And again, I emphasize here, all the active transactions are going to be listed. All the transactions that are still active, they're still working. They didn't commit. They didn't say we have done. We're still working. Okay. Then flash the log. This optional. Here the most important thing, there's a difference here. So write all the database elements that were updated by all transactions that are still in memory buffer. What do you mean here by all transactions? Remember, this undo and redo. That means I need to keep all the change that has been done by any active, or let's say inactive transaction, or committed transaction or uncommitted transaction. That's why we said all. Okay, this is the main difference between like the non-quiescent and checkpoint. For redo and for undo and redo. For the redo, we have the same rule, but the same procedure, but we have only updated by the committed transaction. Here, undo and redo must be by all transactions. And this makes sense because I need to find a way of keep tracking for two different pieces of information. The uncommitted transaction for undo and committed transaction for redo. Okay, so since we write all and for the checkpoint, what the goal here, try to reduce the size of the log entry or the log file by eliminating the committed transaction. So between the start checkpoint and the end checkpoint, I will make sure that all the change has been done or modified by, or any database elements has been modified by any transaction. We must reflect a change to the disk. Okay, then after that, flush the log. So this is an example. Okay, so seeing that we decide, yeah, it's perfect time to start the checkpoint. Then in this case, we have I need just to list, the active transactions. For example, in this case, only we have T2 because T1 is commit. Okay, then after that, I need to do what? I need to make sure the end checkpoint log record. When after I make sure that all the change has been done by by both transactions must be reflected to the disk. So here after start checkpoint, what the database management system do here is to check, do we have any database elements modified in the, and still there's the modification still in the main memory? Yes, that means you have to reflect to the disk. How can you tell here? I will go back and check whatever database elements has been modified. We have the A and we have the B. Okay, they have been modified. So in this case, between start and end checkpoint, I need just to reflect that in the disk. That means I need to make sure that we have to write, or to say output A and output B in the disk. That means it might be at the time A and B modified still the main memory, so make sure that must be written in the disk. Even someone said, but we have a commit transaction. Yes, but we cannot guarantee if you commit transaction, that means you are going to reflect the change to the disk. That's why we have to make sure that is reflected to the disk. So if you found the end checkpoint, what does that mean? Again, any transaction or any database element has been modified before, for the committed transaction before the start checkpoint has been guaranteed or ensured that the change has been reflected to the disk. And also, any database element has been modified before the start checkpoint for uncommitted transaction has been a change. So has been updated or modified or reflected the disk. Okay? So this is, example T2. That's maybe then after that, maybe T2 has modified another database element. I didn't care about this one here between the start checkpoint and end checkpoint. I need to make sure that which database elements has been modified by uncommitted and committed transaction before this point. Okay, so in this case, I need A and only B. How about C? C happened after the start checkpoint, so I'm not gonna touch this one. Okay, then again, this non-quiescent, checkpoints that we allow, to accept new, let's say, transactions, so new transaction can be start and etc. Okay. So recovery algorithm in general, so we need to redo the committed transaction and we need to undo the uncommitted transaction. How can we perform that? So how to redo the committed transaction in case one? So again, we have two scenarios. Remember that we have two cases: either start at the back, scan backwards, either gonna find end checkpoint or start checkpoint. So we find, say, the end checkpoint log record first. Okay, what does that mean here? That means all the update has been done for any for the committed transactions has been reflected at disk. Even for uncommitted transaction has been reflected at disk. That's happened before the start checkpoint. Okay, so in this case, it looks like I'm repeating myself. That means all the actions that has been committed before the start checkpoint record need not to be redone, which makes sense, yeah, because for all the committed transactions here before the start checkpoint, do you need to redo them? If you found the end checkpoint, no, because remember, we are not gonna list or put the end checkpoint. It's gonna be logged in the log record, in the log entry, before I make sure all the change have been done by the, let's say, the committed transaction has been written to the disk. That's means in this case I don't need to redo this one again. Okay, so all the portion of the data that belongs to the committed transaction, we are not going to touch this one. So it looks like we have talked about, the recovery using the non-quiescent, checkpoint using redo here. Okay. And remember, this is undo redo, but right now I'm talking about how can we perform redo. Remember, we said we have committed and uncommitted. It looks like we need to split this one in two parts. How can you deal with the committed transaction, and how can we deal with the uncommitted transaction? Okay. So how about the committed transaction that were active in the start checkpoint need only to return starting from the start checkpoint. For example, if you have any, let's say you start from the back here. And yeah, let me hear the example here. We have at the time that when you start the start checkpoint T1, when you start the checkpoint T1 was, let's say, active at the time. But after that, the T1 is commit, either at this point or here, anywhere. Okay? In other words, it's committed after we start the checkpoint. How can we recover from this one? Or recover if the system's crashed? In this case, I need to do what here? I need just to recover, repeat or redo all the operation that belongs, or that this transaction has been committed or done that start after the start checkpoint. Did you give me a quick example here? So assume that just example here, we have, let's say, the start check point, for example, and we have T1, for example, or T2. We have more, okay? But just I'm choosing T1. It's a start, okay? I cannot change now. Anyway, then after that we have, let's say here the end. This end the checkpoint. The T2 start at the time is checkpoint. I hate that. Anyway, this is start checkpoint. We have the T1. And end the TA, either in this point here or here, anywhere here, we have a commit. Let's say T1. This is a commit T1, okay? So, T2, sorry. In order to recover this one, this is undo. So I'm gonna start backwards here. I found in the checkpoint and go back until I find this one. Okay, this is fine that we have a start checkpoint and T2 was active at the time. I need to redo the T2 because T2 is a commit transaction. So we have two options. Either I need to commit all the operation, redo all the operation that has been done that by the transaction T2, or I'm going to utilize the property that I got from the non-quiescent checkpoint. In this case, the non-quiescent that if you found in the checkpoint, here, this means all the transaction was active and or committed at that start checkpoint, all the change has been reflected to the disk. That means we guarantee, for example, in this case for the T2, all the activity, or they say write or modification or updated for the database element done by this transaction, definitely written at the disk. That means don't do, let's say there is no need in order to update or redo, all the updates that has been made by this transaction before the start checkpoint. In order to recover this one, redo this one, start doing this operation after the start checkpoint. Because in this part, whatever database element has been modified or updated by the transaction T2, we cannot guarantee that the change has been reflected in this. So now let's take a look. I'm still going to talk about the non-quiescent checkpoint for undo redo. But now let's take a look how can we deal what we have to do, for example, for uncommitted transaction. We need to undo them. Okay, so we still have in this case one, if we find, for example, the end checkpoint. Okay, that means here you know that all the updated has been done by the uncommitted transaction has been before the start checkpoint has been modified or updated to the disk or reflect to the disk or written to the disk. That means here I need to do what? When you need to redo them, I need to go back a little bit here. Yeah? Because whatever for the transaction T1 and T2 at the time, since assume that both of them are not committed, this means we modify some database elements. So we modify the database element. We need to redo or undo their action. This means I need to go back until the first or earliest start with the TR. So it looks like I need to do undo this case. I mean the same case that we recover using the undo. Okay. How far we can go back? So you can maybe you need to go back to the previous start checkpoint. So keeping go back. Maybe the moment that you're gonna stop here until the previous start checkpoint. Okay. And as an example here, for example, we have a T1 start before the start checkpoint. Then here we decide that we need to, add the start checkpoint, and this is the end checkpoint. You know that. That means all the database elements modified by data. The transaction T1 and T2 has been reflected to the disk before the disk. So for the T1, for example, we modify all the database X. Okay. Then here definitely we perform the auto. That means this is the search area I need to look at. Try to find the earliest start checkpoint for the transaction. It depends. Here maybe you have T1, T2, T3, maybe T2 before the T1 or whatever. You need just to find the earliest start point for the transaction, and this is going to be my search area. What do I mean by search area? That means I need to scan for backwards, and I need to undo all the transaction. That I can uncommit the transaction that I'm going to find between this point up to this point. So again, using these, the checkpoint to reduce, instead we have to look into the entire log file. I have only portion of the data I need to look at. Just summarize, what we have done or learn right now for the case one. Case one, remember, that means you start backwards, scanning, and you find the end checkpoint. And I'm talking about the undo and the redo log file here. So in this case, for the scan up for the committed transaction. Remember, we have a committed and uncommitted. For the committed transaction, I need to do what here? I need to scan up to the start checkpoint, yeah, T1 up to TK record. Then you need to identify all the committed transactions. And you know that if you find the end checkpoint, that means I'm fine. All the, action, or let's say the database elements that are touched or modified by the committed transaction has been what? Has been, reflected to the disk. So I need to find out or identify the committed transaction after this, up to the start checkpoint. Then after that, I need to redo all the change starting from this point. Any change before this point, we guarantee that because we have the end checkpoint that has been committed to the disk. That means don't waste your time, do it again. This is for the committed transaction. So how about the uncommitted transaction here? A scan up to the earliest TI. What's the TI? This one element transaction that is going to be listed in the start checkpoint was active at that time. Well, that means it was uncommitted at that time. Then after that, you need to do what? If the TI is uncommitted, transaction must be uncommitted, because if it's committed, that means I can deal with this one with the situation. If it's not uncommitted, that means I need to deal with the situation in this part. That means I need to undo all the action for the uncommitted transaction that after the start checkpoint too. Okay? Sorry, after the start TI. That means in this case, you need just to identify where the search area that you need to work with. Clear, guys? So this is case one. How about the case two? Case two, that means you start scanning backwards, but you didn't find, the end checkpoint. So what we did here, we found only, the start checkpoint. That means the last time that you tried to start, these non-quiescent checkpoint, we failed. The system crashed. So we don't have any more information. In other words, that means it looks like we didn't have such checkpoint. So it looks like we need to do recovery similar to the case one. Keep scanning until we find the end checkpoint that belongs to the previous successful, the start checkpoint. Then after that, do the same thing that we did in the case one. So let's have example here. And this is one example that you expect in the exam, something like this. Of course, this is a simple one. The exam is going to be larger, okay? And let me tell you something about that. Sometimes maybe I'm going to miss these elements that is going to be here. For example, let's say I'm not going to ask you that means you have to do the start checkpoint. No, I'm gonna tell you, for example, we decide to add the start checkpoint after operation 5. I'm gonna have a count, let's say 1, 2, 3, 4, 5, etc. to make it easy for you. For example, after the log enter, after operation 5 or whatever, that we decide to add start checkpoint. You need to tell me, for example, what the list of the transaction you have to list it here. So this one, maybe it's gonna be blank. That's one question you expect. That means you have to fill this one. You need to make sure that you fill this one with the right transaction. That means if you decide to have the start checkpoint here, so take a look at this one. What the active transaction at time, and at that time we have only T2 because T2 is the only one that hasn't been committed. It's not completed. It's still working. It's not a port. It's not commit. So I have to list this one here. Okay. At the beginning, generally speaking, I will give you, for example, if you have different database elements, I'm going to be initially the database element initial value, for example, A equal 5, 4, for example, B is equal 9, C equal 14, and D equal 19. Something like this. Or also, you can deduce this information because if you give you this entry, you know that the first time they modified the database elements here, I said, well, this is the old value, this is the new value. So you can tell this is the old value 4 and the new value 5. So you can say the initial value of A is 4. And the same thing for the B and etc. Suppose the system cache after, let's say, writing both commit record. For example, after you perform this operation, the system cache here. Then I'm gonna say what we have here is, this is undo and redo log. And please make sure that you are working with the right log file. For example, sometimes maybe I will give you undo log, or maybe give you the redo log, or maybe give you undo redo log. So each of them, they have different way to work with, yeah? Okay. So for the undo, redo log together. So in this case, if the system fails here, what we have to do here, remember, this undo redo log. That means we need to undo the uncommitted transaction, and you need to redo the committed transaction. Yeah. So in this case, you can divide this one 2 parts. You can 2 lines or whatever, 2 bars or 2 columns. So you need to identify the committed transaction that you have. And since we have to start the scan from the end, I faced what first? I found the end checkpoint. Oh, if I found the checkpoint, that's perfect. Because for the end checkpoint, that means I know this undo redo log. I know this is going to be non-quiescent, checkpoint. That's what we give you. We're not going to cover the quiescent anymore because we give you just example, and non-quiescent is, our options here. So in this case, I know that end checkpoint I know how the let's say the non-quiescent checkpoint works. I know that if you have the undo and redo log file and creator will come up with a non-quiescent checkpoint. That means if you found any checkpoint, that means all the committed transaction and any action or modified database element has been modified before start checkpoint has the change or has been written to the desk. So for the committed transaction, I did identify back. End checkpoint, I will go back up to the start checkpoint in order to identify whether you have committed transaction or uncommitted transaction. So in this case, I can identify we have a committed transaction, we have T2, T1 is definitely T1 is committed, and we do have T2 here because the T2 is committed here. Okay? Sorry, let's go back. I have T2 and T3 as the committed transaction because I start from here, I go back up to this point. What do you have a commit? I found T2 and T3. Okay. Do you have any uncommitted transaction? In other words, do you have any transaction? So that means look at T2 here and T3. They were used to be active at the time. So do you have any uncommitted transaction? No, because you have T2 and T3, then both of them are committed here. Okay. So how can we deal with the committed transaction? How can you deal with the uncommitted transaction? We are lucky we don't have uncommitted. So let's take a look. How can we deal with the committed transaction? Remember, the committed transaction, that means you have to do what? Starting from the start checkpoint. I don't care about anything before this point. So that means I need to redo the action from the T2 to T2 starting from the start checkpoint. Yeah. So in this case, I'm gonna take a look what? Starting with the beginning, you have to do this one in the forward. Yeah. Not in the reverse order, in the forward order. So T2 is going to be here. We'll start in the first C equal what? What's the new value of this one? C is updated C equal 15. This is the old value. This is the new value. Then go back here. D is equal what? Is equal 20 because this is the new value and this is the old value and this is redo operation. I'm done. Someone maybe wonder and say, how about this B? Because I modified this one before. But remember, since we have empty checkpoint, we guarantee that for all the transactions that was active or either is going to be committed or uncommitted, all the database element has been modified by all the transactions must be committed to the disk, must be reflect to the disk. So we already guarantee that the value of P's that made modified by transaction 2 is modified to the new value, so it's equal 10. Okay? Undo, we don't have any problem. So okay, we have the same example here, and assume that the cache happened in this one. And sometimes I'm going to tell you the cache is going to be happen after writing specific commands. And to make it easier again for you, I'm going to give you like line number here. So I say maybe the cache happened, for example, after after line 10 or line 15. Yeah, so it's easy for you to do. So the cache is going to happen at this point, for example. So what do we have here? I'm going to scan from the end, the same thing, backwards. I found any checkpoint. Okay, good note, good point. So I go back up to the start checkpoint, and I know it's undo redo log. Yeah. So in this case, I need to identify. Looks like I need to identify what do I have a committed transaction, uncommitted transaction. What's the committed transaction in this case? It's going to be here. We have only T2. Yeah. Do you have any uncommitted transaction? Yes, it's T3 because you start here. I didn't see any commit or abort here. So in this case, what we have to do, I need to do, so this means I need to redo T2 and I need to undo T3. Yeah. Let's go one by one. For the redo portion, you have to start from what? Redo from the start checkpoint, and again, because we have end checkpoint, there's no guarantee any change has been done by this transaction. It's definitely going to be reflected to the disk because we have end checkpoint. So the only thing I need to do is start from the start checkpoint and redo all the committed transaction. So what's the committed transaction? T2, that means C updated to the 15. Do you have anything else? No, I don't have anything. Maybe you have more operation, you have to continue this one. If you don't have any more operation, then done. This is for the committed transaction. Now let's take a look at the undo portion, which is interesting here. So I mean here, take a look here. It's T3, does the T3 mention here or not? If it's not, that means it start, this means all the portion of the data before the start checkpoint, I don't need this one. Yeah? Because when you need to redo T3, I need to identify the first start, the earliest start T point, I mean TI or transaction, which in this case started from this point, and I need to redo this one from the end up to this point in the reverse order. So I didn't need to go back before the start checkpoint because at that time T3 wasn't active. Yeah? So in this case, I'm going to start the scan from here up to this point, or up to you find the start T3 in the reverse order. Go back here. Do you have anything to reverse order? For example, maybe you have T3 going to modify multiple database elements here. You have to do this one. You have to give me the right order of the update or the undo or redo. Okay. So here, since we have only D, only one database element has been modified by the database, or let's say the transaction D, T3, so in this case I need to update this one with the old value. You know, remember, make sure that this is the old value, so D equal 19, not 20, because redo. Assume that we have one transaction here for F, for example, T3, F1 and 0, for example. So if you do this one in reverse order, this means you have to say first update F with 1, then after that update D with 19, because you have shown me that in the reverse order. If you give me this in the wrong order, you're going to lose points. Okay? So, again, expect that to give you a long one. So this is the question that's related to undo, redo, and maybe undo, maybe redo. Maybe the question has different parts. For example, assume that you are going to take a look, only you have undo log file. Then after that, give you another question based has undo log file. Then after that, they're going to say, what if you have undo, redo log, then how to deal with this one. Again, if you understand these slides, then you don't have a problem with this part of the, the exam. The exam or the question related to this question, this part. So what we learned so far here, we talk about the consistency of data. We have, just cover one source of the problem. Unfortunately, I don't have time to cover most, the concurrency control and etc. and log it. So we reach, I guess, yeah, this is the last slide of the lecture. Finally, you are gonna get rid of me. You're not gonna, hopefully you're not gonna take any course with me anymore. So we reach the last slide. Hopefully I try to do my best to cover the material. Hopefully you learn something useful. Hopefully by the end of the semester, maybe you change your idea about how the database management system works. Hopefully this one's gonna help you in order to build, let's say, or write your SQL query in more efficient way. And that's all, guys, for today. It's too short for you. Please prepare for the final exam well. Please try to do your own work. Okay, you have only 4 hours to finish the final exam. It doesn't mean that you have to spend 4 hours to finish the exam. I guess, my expectation that you're gonna finish the exam in 2 hours. So I give you another or extra 2 hours just to make sure that you can, finalize your answers. Okay, handwritten, typing, whatever, it's fine. Even if you write in a piece of paper, then take a picture for the image for your answer, it's fine. It's perfect for me. Okay, I got a question about what the difference between, the operating system and the database system. Remember that we're starting with the first day, we start to say, what if we try to build the database system without using the database management system here? We are trying to rely on the operating system, and we figure out it's not a good idea, for many reasons. One example we try to do here, when you talk about the buffer manager, for example, or buffer pool here, or how can we store the data on the disk. Remember, we talk about the record manager, and you talk about the file manager, show you that, or storage manager, we talk about that, how the data is going to be stored. Since the database management system know exactly what the structure of the data, so the database management system know exactly, can expect or can predict what kind of data you need to retrieve from the system. We show you some, scenarios that, for example, if you try to fetch the data from the disk, and if we rely on the operating system, remember that operating system, we have different blocks you need to fetch. You take the first block, the second block, then the operating system maybe gonna thought, this guy is gonna looking for the block number 3 and number 4, and so it's gonna perform the sequential scan, which is gonna lose our buffer manager. But the database management system knows better, because, for example, they're gonna know, for example, this guy is gonna go take buffer 1, block 1, 2, maybe he's gonna jump to the block 3 and 5, and etc. Remember, if we have 3 structures to store our data. Anyway, so we cannot rely 100% on the operating system in order to take care for all the components that we need to build the database management system. Definitely, we need to operate a system somehow. When you try, for example, to store your data in the disk, and you try to fetch the data from the disk, in this case, that the lower, let's say, operation that you're gonna done, like system calls, for example, how can you fetch the byte from whatever from the disk? How can we ask the move the data from the disk through the passes and the memory to the main memory, etc. These are going to be covered by the operating system, but most of the work is going to be done by the database management system. That's all, guys. Thank you very much. Please stay safe, stay home, and hopefully, as I mentioned, you learned something useful in this class, and I appreciate the chance that you get to be one of my students during this course. Thank you very much, and enjoy the rest of the semester. Okay, have a nice day. Bye.